Welcome to this underwater journey into the world of trout. Tonight, we're going to explore together the secret life of one of nature's most fascinating cold water creatures. Over the next couple of hours, we'll wade through streams of knowledge, drift along currents of discovery, and learn more than 100 facts about these remarkable fish. And you don't have to worry about remembering any of it. Just let the words wash over you like cool water over smooth stones. Let your mind wander where it wants to go. And if you drift off to sleep, somewhere along the way, well, that's exactly what we're here for. So get comfortable, settle in, take a deep breath, and let's begin our journey with the trout itself, what it is, where it comes from, and the incredible life it lives. Let's start at the very beginning with a simple question. What exactly is a trout? A trout is a member of the family Salmonidae. That's a rather formal way of saying that trout are cousins to salmon. Close relatives, actually. Part of the same extended family tree that branches throughout the cold waters of our world. They're carnivorous freshwater fish, hunters of the current, and they come in many varieties. Rainbow trout, with their pink stripe and spotted backs. Brown trout, golden and wise-looking. Brook trout, delicate and beautiful. Each species its own character, its own story, but all of them unmistakably trout. These fish are predators, but gentle ones in their way. Patient, they wait in the water, watching, conserving their energy. And when the moment is right, when an insect drifts too close or a smaller fish ventures into range, they strike with surprising speed. We'll get to their hunting habits later. For now, we're just getting to know what a trout is in the most basic sense. Now, here's something interesting. Trout originally come from the northern hemisphere, the upper half of our planet, if you will. That's where they evolved, where they first appeared in the ancient waterways of what would become Europe, Asia, and North America. But if you were to look for trout today, you'd find them almost everywhere. They've been introduced around the world, carried by humans to new continents, new countries, new rivers and lakes they'd never have reached on their own. This spread really picked up steam in the late 1800s, when trout stocking became commonplace. People loved fishing for trout, and so they brought trout with them wherever they went. Rainbow trout in particular have become true citizens of the world. You can find them now on every continent except Antarctica. Imagine that, a fish that started in specific cold streams of the Pacific coast of North America, now swimming in rivers across Asia, Africa, South America, Australia. It's quite a journey for a fish that, in many ways, prefers to stay in the same pool for most of its life. But of all the trout species, one stands out for having the most impressive natural range: the brown trout. Even before humans started moving fish around, brown trout had already conquered an enormous territory on their own. Their native range is, well, it's breathtaking, really. Picture this. Brown trout naturally occur from northern Norway, all the way down to the Atlas Mountains in North Africa. From the tributaries of the White Sea in Russia, in the Arctic Ocean, down to the mountains of Africa. The western edge of their range touches Iceland, out in the North Atlantic, while the eastern limit reaches all the way to Afghanistan and Pakistan, in the tributaries that feed the Aral Sea. That's an extraordinary span of geography, multiple continents, different climate zones, from Arctic waters to Mediterranean streams. Brown trout adapted to all of it long before humans ever thought to carry them elsewhere. They're survivors, these brown trout, flexible and resilient. It's part of what makes them so successful as a species. But let's talk about something more intimate now. The lifespan of a trout. How long does a trout live? The answer, like so many things in nature, is it depends. But typically, trout live somewhere between 4 and 8 years. Rainbow trout, for instance, usually make it 4 to 6 years in the wild. Brown trout tend toward the longer end, averaging about 8 years. Steelhead, which are actually rainbow trout that migrate to the ocean, can live up to 11 years, sometimes spending as many as 7 years in fresh water, and then 3 years in the sea, before returning to spawn. Of course, there are exceptions. The largest rainbow trout ever caught was estimated to be 11 years old, an ancient fish by trout standards, a survivor who'd navigated years of predators, anglers, seasons, and challenges. Most trout don't make it that long. Life in the water is not easy. There are herons and otters, eagles and bears, hooks and nets. There are floods and droughts, warm summers that make the water uncomfortable, cold winters that lock the surface in ice. To live 8 years as a trout is to have been very lucky, or very clever, or perhaps both. Now, when you picture a trout, how big do you imagine it? A foot long? Maybe 2 feet. Most trout species do average between 1 and 2 feet in length. A nice size for a fish, substantial but not overwhelming. But trout can grow much, much larger than that. Rainbow trout, under the right conditions, can reach up to 45 inches in length. That's nearly 4 feet. And they can weigh more than 50 pounds, though typical weights hover around 8 pounds. Imagine encountering a 50-pound trout. That's not a little stream fish anymore. That's a submarine of muscle and appetite, a creature of real power and presence. These giants are rare, of course, found only in the most productive waters. Large lakes or rivers with abundant food and space to grow. But they exist, and they remind us that trout are not just delicate, pretty fish. They can become formidable predators. And speaking of growth, here's where things get really interesting. Trout don't all grow at the same rate, not even close. The speed at which a trout grows depends almost entirely on where it lives and what it eats. The variation is, well, it's dramatic. Consider a young trout living in a cold mountain stream. The water is clear and beautiful, rushing over granite, perfect and pristine. But it's also nutrient poor. Food is scarce. Insects hatch in modest numbers. Small prey fish are few. That trout, after 1 full year of life, might weigh only 20 grams. That's less than an ounce. It's barely grown at all. Now take another trout, the same age, but living in a productive lake, a lake rich with nutrients, full of insects and small fish. Where the water temperature is warmer and the growing season is longer. That trout, after 1 year, might weigh 300 to 500 grams. That's nearly 1.5 pounds. The same species, the same age, but 25 times heavier. Under truly optimal conditions, say in a recirculating aquaculture system where temperature is controlled, food is abundant, and every variable is managed, a rainbow trout can grow from first feeding to 350 grams in just 8 to 9 months. And in nutrient-rich ponds with abundant food, Researchers have documented trout growing 2 inches per month during their first 100 days of life. 2 inches a month. That's explosive growth, the kind of acceleration that transforms a tiny fingerling into a respectable fish in a single summer. It makes you think, doesn't it? About potential, about environment, about how much our circumstances shape what we become. A trout in a barren stream stays small. A trout in a rich lake becomes robust. Same fish, different worlds. Let's shift our focus now to something even more fundamental: the structure of the trout itself, the skeleton, the framework that holds everything together. A rainbow trout has approximately 262 bones. Let that sink in for a moment. 262. That's a lot of bones for a creature that might fit in your hand. 62 of those bones are vertebrae, running from the head all the way down the spinal column to the tail. Each vertebra is a small, intricate piece of calcium architecture, and from each one extend at least 2 more bones, sometimes more. There are between 27 and 30 pairs of large rib bones on the bottom of the fish, protecting the internal organs. Another 27 to 30 bones arch over the top of the spinal column. And then there are the pin bones, those troublesome little things that anyone who's eaten a trout knows about. Approximately 17 intramuscular floating pin bones on each side of the fish, tucked into the flesh. The vertebrae count in rainbow trout normally ranges from 59 to 63, though in some populations you'll find variation from 57 all the way up to 67. It's fascinating how even something as fundamental as the number of vertebrae can vary slightly from one population to another, shaped by genetics and environment over countless generations. This skeleton of the trout is not simple. It's complex, elegant, evolved over millions of years to do exactly what it needs to do. The trout skeleton consists of an axial skeleton, that's the skull, and the vertebral column, and an appendicular skeleton that supports all the fins. The skull alone is a marvel of engineering. It's made up of a central cranium and many other bones that aren't tightly connected to each other. This loose connection is intentional, designed that way. It allows the bones to move as the trout breathes, as it opens and closes its mouth, as it feeds. The skull flexes and shifts, a mechanical system of levers and hinges all working together. And those pin bones we mentioned, they're not just annoying for people trying to eat fish. They serve a purpose. They're horizontal calcified bones that come off the vertebrae, and they have nerve endings in them. Those nerve endings sense the proximity of other fish nearby. They're part of the trout's awareness system, helping it detect movement and presence in the water around it. Every part of the trout's body has a reason, a function, nothing wasted. Finally, let's talk about muscle, the engine that powers a trout through the water. The muscle composition of a trout is approximately 60% white muscle and 10% red muscle. The remaining 30% is other tissues, organs, bones, skin, everything else that makes up a living fish. That muscle mass, overall, accounts for about 60% of the fish's total mass. So a trout is, in a very real sense, mostly muscle. It's built for movement. Now, that white muscle, that's fast twitch muscle. It's what gives a trout its explosive speed, its ability to dart forward in a split second to catch prey or escape danger, At least 70% of all the muscle in a trout is this white, fast-twitch type. In most freshwater trout, white muscle comprises about 90% of the total muscle mass. It's powerful, but it fatigues quickly. You can't run on fast-twitch muscle for long. It's for bursts, for moments of intensity. The red muscle is different. Red muscle lies directly under the skin, along the side of the body, a thin layer you might not even notice unless you're looking for it. It contains smaller diameter cells, more mitochondria, those little powerhouses that produce energy. It has higher myoglobin content, which gives it that reddish color and helps it hold oxygen. And it contains more lipid droplets, stored fat for sustained energy. Red muscle is for endurance, for the steady, constant work of holding position in a current, of swimming upstream during migration, of sustaining effort over time. So a trout is built for both, for explosive speed when needed, and for endurance when required. It's a beautiful balance, really, encoded in the very fibers of its being. And that, friends, is where we'll pause for now. We've begun to understand what a trout is. A member of the salmon family. A cold water predator with ancient roots in the northern hemisphere, but now found across the globe. We've learned about their lifespan, their size, how they grow in different environments. We've explored the intricate skeleton that supports them and the powerful muscles that drive them through the water. There's so much more to discover, but we have all night. Rest your eyes if you need to. Let your breathing slow. We'll continue this journey together, drifting gently through the secret life of trout. Chapter 2. Welcome back, or perhaps you never left. Perhaps you've just been floating here with us, half awake, half dreaming. That's perfectly fine. We're continuing our gentle exploration of the trout. And in this part of our journey, we're going to look at how these fish actually live in the water, how they breathe, how they float, how they move through their liquid world with such grace and efficiency. So settle back in, let your thoughts drift, and let's wade a little deeper into the secret life of trout. Let's begin with something that might seem simple, but is actually quite remarkable. How a trout floats. How does a creature denser than water manage to hover effortlessly in a current, neither sinking to the bottom nor bobbing to the surface? The answer lies in an organ called the swim bladder, and trout have a particularly interesting version of it. Trout possess what's called a physostomous swim bladder, which is just a technical way of saying it's an open swim bladder, one that's connected directly to their digestive tract. There's a pneumatic duct, a small tube running from the swim bladder to the esophagus and gut. This might sound like a strange design, but it's actually quite clever. It means a trout can gulp air at the surface to inflate its swim bladder, filling it like a tiny balloon inside its body to gain buoyancy. And when it needs to sink or descend, it can burp. Yes, burp, or release that air to deflate the bladder rapidly. If you've ever seen lake trout being pulled up from deep water, you might have noticed them bubbling as they reach the surface. That's their swim bladder adjusting, releasing gas as the pressure changes. It's a quick, efficient system that gives trout precise control over their position in the water column. They can rise, sink, hover, all by adjusting the air in that internal bladder. It's like having a built-in buoyancy compensator, the kind scuba divers use, but evolved and perfected over millions of years. Now, floating is one thing, but to live in water, a trout needs to breathe. And breathing underwater is a very different challenge than breathing air. Trout, like all fish, extract oxygen from water using their gills. But what makes trout particularly impressive is just how efficient their gills are at this task. Trout gills can extract over 80% of the available oxygen from the water that passes over them. 80%. That's extraordinary. By comparison, human lungs extract only about 25% of the oxygen from the air we breathe. We're wasteful breathers compared to trout. How do they achieve this? Through something called countercurrent exchange, and it's one of nature's most elegant solutions to a difficult problem. The gills themselves consist of thin filaments covered by lamellae, little plate-like structures packed with dense networks of capillaries, the tiniest blood vessels. Now here's the clever part. Blood flows through these gill capillaries in the opposite direction to the water flow. Water flows one way over the gills. Blood flows the other way through the capillaries inside them. This opposite direction flow, this countercurrent exchange, means that the blood is continuously encountering water that has higher oxygen concentration than the blood itself. Even blood that's already picked up quite a bit of oxygen keeps meeting water that still has more to give. It's a continuous gradient, an ongoing opportunity for oxygen to diffuse from water into blood. If the flows went in the same direction, they'd equalize quickly and oxygen transfer would drop off. But with countercurrent exchange, efficiency stays high all the way through. It's beautiful, really, a solution so elegant that engineers have copied it in heat exchangers and other industrial applications. But trout figured it out first, hundreds of millions of years ago. There's another fascinating detail about these gill lamellae. The spacing between them, how close together they're packed, is optimized in a very specific way. The densely packed structure provides a large surface area for oxygen to diffuse across, which is good. But it also creates considerable resistance to water flow, which is bad. The trout has to pump water through those gills, and the tighter the spacing, the harder it has to pump. Studies show that the distance between lamellae varies very little among fish species, even among fish with vastly different body sizes. This represents an evolutionary optimization. Millions of years of natural selection finding the sweet spot that maximizes oxygen transfer for a given amount of pumping pressure. Too far apart, and you lose surface area. Too close together, and the resistance becomes too great, requiring too much energy to pump water through. More active fish species, the ones that swim constantly, the ones that need more oxygen, tend to have thinner, more abundant, and more closely spaced lamellae. They pay the cost in pumping effort, but they gain the benefit of higher oxygen extraction. Trout, as active cold water predators, fall into this category. They've evolved gills that can support their energetic lifestyle. Let's come to the surface now, to the outside of the fish. What does a trout feel like if you touch one? Trout are covered in tiny, clear scales and a protective slime coat. The scales themselves are very small and thin, so thin they're often invisible to the naked eye. They begin to form when a trout reaches a few inches in length, growing in layers like the rings of a tree. In fact, you can age a trout by examining its scales under a microscope and counting the growth rings. But it's the slime coat that you'd notice first. that slippery, slightly mucus-like coating that covers the entire body. It might seem unpleasant at first thought, but this slime is crucial. It's actually a glycoprotein mixed with water, and it serves multiple vital functions. First, it provides protection from fungal and bacterial infections. The slime creates a barrier between the trout's skin and the water full of potential pathogens. Without it, a trout would be constantly vulnerable to disease. Second, and perhaps more surprisingly, it reduces drag while swimming. That slippery coating helps the water flow smoothly over the trout's body, potentially cutting friction by up to 65%. 65%. That's enormous. It means a trout can swim faster and more efficiently, using less energy to move through the water. It's like having a permanent coating of some high-tech lubricant, except it's self-producing and self-maintaining. This is why, if you ever handle a trout, you want to wet your hands first and touch it as little as possible. That slime coat is precious. Removing too much of it can leave the fish vulnerable. Now let's talk about something a bit more fierce: the teeth of a trout. All trout have sharp, recurved teeth designed for grasping prey. Recurved means they curve backward toward the throat, which makes them excellent at holding onto struggling prey. Once something is caught in a trout's mouth, those backward curving teeth make it very difficult to escape. Trout don't just have one row of teeth either. They have multiple rows. There are canine-like teeth on both the upper and lower jaws, pointy and prominent. And then there are specialized vomerine teeth on the roof of the mouth. The vomer is a bone in the center of the palate, and having teeth there provides extra gripping power. Brown trout, it turns out, have the largest and most impressive teeth of the commonly caught trout species. They use these formidable teeth to hold onto fish, frogs, crayfish, and even mice. Yes, mice. Large brown trout are opportunistic predators, and if a mouse happens to fall into the water and start swimming, well, that's just protein. Those teeth clamp down and the mouse disappears. Here's another interesting detail. Trout can regrow individual teeth if they're lost or pulled out. Lose a tooth fighting with prey or biting down on something hard. No problem. Another one will grow in to replace it. It's a useful adaptation for a predator whose survival depends on its ability to catch and hold prey. And trout spend a lot of time using those teeth because they spend most of their time searching for food. Trout are carnivores that dedicate up to 80% of their day to the hunt. 80%. Imagine spending 4/5 of your waking hours just looking for your next meal. It's a full-time job being a trout. Their diet is varied. Smaller fish eggs when they can find them. Crustaceans like scuds and crayfish. Insects, mayflies, caddisflies, stoneflies, both adults and larvae. And small fish, minnows, sculpins, even smaller trout. They're opportunistic, taking whatever prey is available and worth the energy expenditure to catch. Let's shift now to appearance, to the way trout look as they grow from young to old. Juvenile trout display distinctive parr marks that fade as they mature. If you've ever seen a young trout, you've probably noticed these: dark vertical marks or stripes along their sides, regularly spaced like bars on a fence. All young salmon, trout, and their relatives have them. These parr marks serve as camouflage. They break up the silhouette of the fish, making it harder for predators to distinguish the trout's shape against gravel and submerged branches. For a small fish hiding around root wads and other structure, trying not to be eaten by a heron or a larger fish, this camouflage is life-saving. The marks are oval-shaped, pronounced in juveniles, and they gradually lighten and disappear as trout grow into adulthood. It's like shedding childhood clothing as you grow up. Though, interestingly, some species never fully outgrow their parr marks. The McCloud River redband trout, for instance, keeps faint parr marks throughout its life, a permanent reminder of youth. And speaking of appearance, different trout species have distinctive color patterns that make them recognizable even to a casual observer. Brook trout, which aren't technically trout at all, but char, though that's a story for another time, have red spots encircled by bluish halos and beautiful worm-like markings along their back. They look almost hand-painted, delicate and ornate. Brown trout have large black spots scattered across their bodies, and red or orange spots encased in lighter halos. They're more subdued in color than brook trout, more earth-toned, but elegant in their own way. Rainbow trout feature a broad, reddish-pink stripe running horizontally down each side of their body, like someone took a paintbrush and drew a line from head to tail. It's this stripe that gives them their name, though the intensity of the color varies depending on the fish's diet, health, and breeding condition. And cutthroat trout are named for the vivid red or orange slash-like marks on the underside of their lower jaw, as if someone had made a small cut there and the fish had bled just a little. It's a distinctive marking, impossible to mistake once you've seen it. All of these patterns evolved for specific reasons: camouflage, species recognition, sexual selection. Yeah, but they also make trout beautiful. There's an aesthetic pleasure in looking at a healthy trout, in seeing the spots and colors arranged across its body. Let's talk now about movement, about speed. Trout can swim at remarkable speeds, reaching over 3.5 meters per second in short bursts. 3.5 meters per second is about 7.9 miles per hour. That might not sound like much compared to a car, but remember, water is much denser than air. Swimming through water at that speed requires tremendous power. The maximum observed swim speed for West Slope cutthroat trout is 3.55 meters per second. Rainbow trout can reach 2.72 meters per second, about 6 miles per hour. These are sprint speeds used for chasing prey or escaping danger. Trout can't maintain them for long. Remember that white, fast-twitch muscle we talked about earlier? But for short bursts, they're incredibly fast. Brook trout and brown trout can attain absolute sprint speeds exceeding 300 centimeters per second. That's roughly 28 body lengths per second. Imagine swimming 28 times your own body length in a single second. It's explosive, almost violent in its intensity. But that's what predation requires sometimes. That's what escape requires. Of course, most of the time, trout swim much more slowly. The overall average sustained swimming speed for most species hovers around 0.84 meters per second, a comfortable cruising pace that they can maintain for hours if necessary. In their ecosystems, trout play a role much larger than their size might suggest. Trout are keystone species in aquatic ecosystems. The term keystone refers to the central stone in an arch, the one that holds all the others in place. Remove it, and the whole structure collapses. As mid-level predators, trout maintain ecosystem balance. They prey on smaller aquatic animals, insects, small fish, crustaceans, keeping those populations in check. But they also serve as important food for larger predators. Otters, bears, eagles, ospreys, all of them depend on trout as a food source. And when trout die naturally, their remains provide nutrients for scavengers and for the riparian plants growing along the water's edge. Nutrients from the water return to the land, completing cycles that have been going on for thousands of years. Remove trout from a stream, and the whole system can shift. Insect populations might explode. Other fish might overpopulate. Predators might struggle to find food. The balance tips, sometimes in unexpected ways. Finally, let's talk about migration, about the urge that drives trout to travel. Most trout are potamodromous. That's a wonderful word, isn't it? It means they spend their entire lives in freshwater, but still migrate, usually upstream to spawn in the shallow gravel beds of smaller headwater creeks. They're born in one part of a river system, grow up in another, and then return to the headwaters when it's time to reproduce. However, some trout are different. Some species, like steelhead and sea trout, are anadromous. They're born in freshwater, yes, but then they migrate to the ocean. They can spend years in the sea, growing large on the abundant food available there, before returning to freshwater to spawn. It's an incredible journey, from small stream to vast ocean and back again. Navigating by senses we still don't fully understand. These ocean-going trout grow much larger than their landlocked relatives. The ocean is a rich feeding ground, and the trout take full advantage of it. But the journey is dangerous. Many don't survive. Those that do return, however, are impressive creatures, powerful silver, filled with the vitality of the sea. And that, friends, is where we'll rest for now. We've explored how trout breathe, how they float, how they protect themselves with scales and slime. We've examined their teeth, their hunting habits, their beautiful markings. We've marveled at their speed and considered their crucial role in the ecosystems they inhabit. The night is still young. The journey continues. But for now, let your mind rest on the image of a trout holding steady in a current, gills working rhythmically, always searching, always aware, perfectly adapted to its world. We'll be here when you're ready to continue. Chapter 3. We're back now, drifting further into the life of the trout. If you've been sleeping, welcome back. If you've been awake, welcome still. There's no right way to experience this journey. Only your way, at your own pace, in your own state of consciousness. In this part of our exploration, we're going to witness something fundamental, something ancient. We're going to watch trout prepare to create the next generation. We're going to see how life begins in cold, clear water, in gravel beds carefully chosen and fiercely defended. So breathe slowly. Let the images form in your mind. And let's continue. Let's start with something that makes trout different from their salmon cousins. Something that gives them a second chance, and sometimes a third, and sometimes more. Some trout can spawn multiple times in their lifetime. Unlike salmon, who make that heroic journey upstream, spawn once, and die. Their bodies giving nutrients back to the stream, many trout survive spawning. Steelhead trout, for instance, can spawn, return to the ocean, and then migrate back upstream to spawn again, and again. throughout their lives, if they're lucky and strong. Brown trout also spawn each year once they reach sexual maturity. Year after year, when the conditions are right, when the water cools and the days shorten, they feel that ancient urge and make their way to the spawning grounds. It's exhausting, dangerous work, but they survive it. They return to their territories, recover, feed, and when the season comes around again, they do it all over. It's a different strategy than salmon's single, sacrificial spawn. Neither is better or worse. They're just different ways of ensuring the next generation survives. Trout bet on longevity, on multiple chances to reproduce. Salmon bet everything on one perfect moment. Now, as spawning season approaches, something changes in trout. They become different creatures, more aggressive, more focused. Because trout exhibit strong territorial behavior year-round, but during spawning season, this territoriality intensifies dramatically. Large trout are highly territorial. They will aggressively defend their living spaces and hunting spaces from other trout and from other fish species. Sometimes they'll strike smaller fish that encroach on their territory, not even to eat them, but simply to assert ownership. It's a message. This space is mine. Leave. It's similar in a way to how a grizzly bear defends her cubs. It's not about hunger. It's about territory, about dominance, about maintaining order in a world where resources are limited and competition is constant. During spawning season, male brown trout become especially territorial and aggressive. They develop physical changes to match this aggression. Hooked jaws, thicker bodies, darker colors, and they compete fiercely for the best spawning habitat, for the right to pass their genes forward. Speaking of those hooked jaws, let's talk about one of the most dramatic physical transformations trout undergo: the development of the kype. Male trout develop a prominent kype, a hooked jaw, during spawning season, and it's a weapon designed specifically for combat. This hook-like structure grows at the tip of the lower jaw, developing rapidly from bony needles that proliferate from the dentary bone. It's not decorative, it's functional. Males use this hooked jaw, equipped with strong teeth, to bite and fight other males competing to fertilize eggs. It's hand-to-hand combat, or jaw-to-jaw, really. Males will lock jaws, pushing and biting, trying to drive rivals away from females and reds. The kype gives them leverage, makes their bite more effective, turns their mouth into a more formidable weapon. In some species, particularly those that spawn multiple times, what scientists call iteroparous species, the kype becomes even more interesting. After the breeding season ends, the kype doesn't fully disappear. It's not completely resorbed by the body. Some portion of it remains. And here's where it gets truly remarkable. Kypes can become permanent features that continue growing throughout a male's life. Each spawning season, the kype grows again, adding new growth to what remained from the previous season. This fast-growing skeletal tissue fuses with the dense dentary bone, becoming a permanent and continuously growing structure. Imagine that. A fish that spawns multiple times develops a jaw that becomes more and more exaggerated with each passing year. Old males carry the accumulated growth of every spawning season they've survived. The kype becomes a badge of experience, a record written in bone of how many times they've fought, competed, survived. But before any fighting begins, before kypes clash and eggs are laid, trout must find the right place to spawn. And they're particular about this. Very particular. Brown trout, for instance, prefer spawning in water velocities between 21 and 52 centimeters per second. That's a specific range, not too fast, not too slow. Those studies have found reds in velocities as low as 9 centimeters per second and as high as 118 centimeters per second. The optimal range is clear and consistent. They also spawn in minimum depths of 15 centimeters, about 6 inches, with optimal depths between 50 and 75 centimeters, roughly 2 to 2.5 feet. Again, quite specific. Too shallow, and the eggs might freeze or be exposed during low water. Too deep and other factors become problematic. For comparison, consider their winter habitat preferences. Outside of spawning season, brown trout select much slower water, optimal velocities of just 5.7 to 16 centimeters per second. That's significantly slower than spawning preferences. Winter is for conserving energy, for holding in gentle current. Spawning requires flow, requires oxygen-rich water moving through the gravel. Reds are typically located in highly oxygenated shallow riffles and tailouts of pools. These are specific features of a stream. The tailout is where a pool narrows and shallows before spilling into the next riffle. It's a transition zone, and trout love these places for spawning. They spawn in moving water with depths of 1 to 3 feet that provides adequate oxygen flow to the eggs that will be buried in the gravel. Common locations include those tailouts of pools, gravelly glides, shallow riffles, gravel bars, and areas along stream banks where the substrate is right. You can often spot a fresh red because the gravel appears lighter in color than the surrounding substrate. The female has cleaned it, swept away the algae and silt that normally covers streambed rocks. It's fresh, clean, ready for eggs. And speaking of the female's work, let's talk about how reds are actually built, because it's impressive. Female trout construct reds, spawning nests, in clean gravel using their tail and body. A red is an oval-shaped depression in the stream bed, typically 1 to 3 feet wide. The female excavates it by vigorously sweeping gravel with her caudal fin and body, thrashing and digging, moving surprising amounts of material. She selects sites with sufficient water flow and gravel ranging from pea-sized to golf ball-sized in diameter, about 2 to 3 inches for the larger pieces. This size range is important. Too fine, and the gravel compacts, cutting off oxygen. Too large, and the eggs can slip through into spaces too big, too exposed. The female digs a depression, called a pot, in the gravel. Then she deposits her eggs into this depression, and the male, if he's earned the right through combat with other males, slides in alongside her and releases milt to fertilize those eggs. After fertilization, the female moves upstream slightly and excavates more gravel, which naturally washes downstream and buries the freshly fertilized eggs. This creates a characteristic pattern: a pot where the eggs were laid, a pillow of gravel covering them, and a downstream spill where the excess gravel settles. If you know what to look for, you can read a red like a map, understanding exactly where the eggs lie beneath. Now, during all of this, what are the males doing? Fighting, mostly. Male trout aggressively defend reds and fight other males for dominance during spawning. Activity at spawning sites involves intense competition. Male fish bite and fight for dominance around the redd until a victor emerges and takes position next to the female. The winner guards the redd, attacks intruders, protects the eggs from predators and competing males. When trout detect threats to their redd area, they often move sideways to secure eggs and keep them in the nest. It's defensive behavior, protective behavior. After all that work, the migration, the construction of the redd, the spawning itself, they're not about to let some interloper destroy it all. And here's something interesting. Spawning isn't a one-time event for a female, even within a single season. Female trout may dig multiple redds and lay eggs several times during a weeks-long spawning period. Each female lays eggs multiple times during the spawn, often digging out many redds and attracting the attention and competition of males each time. It's not a single day's work. It's a marathon. The spawning process is quite long, lasting days or weeks. It includes everything: diet changes beforehand, migrating to spawning grounds, digging the redd, spawning, protecting the redd, and then recovering. Spawning is extremely energy intensive. Trout save up energy throughout the entire year for this 1 to 2 week reproductive period. They build fat reserves all summer and fall, storing energy for this moment when they'll need to draw on every reserve they have. How many eggs does a female produce? It depends on her size. Female trout can produce 1,000 to 4,000 eggs, depending on their size. During spawning, females yield anywhere from 1,000 to 4,000 eggs per female, depending on fish size, age, and health. Larger females, the old matriarchs who've survived many years, can produce up to 20,000 eggs. That's an extraordinary number, a testament to their size and health. There's actually a fairly reliable formula. Each female can produce 1,000 to 3,500 eggs per pound of body weight. So a 2-pound trout might produce 3,000 eggs. A 5-pound trout might produce 15,000. Size matters in terms of reproductive output. This is one reason why protecting large, old fish is so important for population health. They're the super spawners, producing vastly more eggs than their smaller counterparts. Once the eggs are fertilized and buried in the gravel, the waiting begins. Trout eggs take 20 to 50 days to hatch, depending on water temperature. After fertilization, the eggs must be incubated until they hatch. The incubation period varies quite a bit, between 20 and 50 days, and the main variable is temperature. Colder water results in longer incubation periods. The development of the embryo slows in cold water. It might take 50 days or even longer in very cold conditions. But warmer water accelerates development. In relatively warm water, still cold by most standards, but warm for trout, eggs might hatch in just 20 days or slightly more. During all this time, the eggs lie hidden beneath the gravel, vulnerable yet protected. And they become more hidden as time passes. Redds become virtually unnoticeable within days after spawning as they silt over, while fresh redds are easily identified by their light-colored clean gravel. They quickly silt over and blend into the surrounding riverbed in just a few days. Algae begins to grow. Sediment settles, Within a week or two, you'd be hard-pressed to distinguish a red from any other section of stream bed unless you knew exactly where to look. By January, most fall-spawning reds are virtually unnoticeable. Yet the eggs remain buried in the gravel, developing slowly in the cold water, and they won't hatch until mid-March, on average. That's months of lying buried, hidden, seemingly gone, but actually very much present. This poses a conservation challenge. Anglers can inadvertently walk through reds with wading boots during winter and spring, crushing buried eggs without realizing it. There's no visible sign that says, "Eggs here, be careful." The red has vanished from view, but the consequences of walking on it are very real. Each crushed egg is a fish that will never be. Finally, after all that waiting, the eggs hatch. Tiny fish emerge, but they're not ready to swim freely yet. 11, also called sac fry, remain dependent on their yolk sac for 1 to 3 weeks after hatching. When trout embryos hatch, they emerge with large yolk sacs attached to their bellies. This yolk sac serves as their sole food source for the first 1 to 3 weeks of life, depending on water temperature. During this 11 stage, the fish lie on their sides in the gravel, flop around in groups, and remain extremely fragile. They're susceptible to predators, to siltation that can suffocate them, to pollution. They're vulnerable in almost every way imaginable. But slowly, as the yolk sac is gradually absorbed, 11s develop the structures they'll need for independent life. Teeth form. A digestive system develops. A functional respiratory system comes online. They're transforming from embryos, dependent on stored food, into fish capable of hunting and eating. Then comes a critical moment in a young trout's life. Swim-up fry must gulp air at the surface to initially inflate their swim bladder. When trout transition from 11 to swim-up fry, once their yolk sacs have been fully absorbed, they instinctively swim to the surface for the first time. It's driven by instinct, this first swim upward toward the light. And when they reach the surface, they gulp air to fill their swim bladders. This is a critical behavior. Without it, they can't control buoyancy properly. They'd struggle to maintain position in the water column, would expend too much energy just staying in place. That gulp of air, that first breath of sorts, though they're still breathing through gills, enables them to become functional fish. Though interestingly, at this stage, they're not yet actively searching for food. They're still drawing on the last energy reserves from the absorbed yolk sac. Feeding will come soon, but first they must master buoyancy, must learn to hold steady in the current. Not all of them make it. Some trout never learn to feed properly and die as what biologists call pinheads, young fish characterized by large heads and small, emaciated bodies. They've mastered swimming, but not feeding, and without food, they slowly starve. Their heads growing normally while their bodies fail to develop. It's a sad end, but it's part of the natural mortality that every generation experiences. Not every egg becomes a fish. Not every 11 becomes a fry. Not every fry survives to adulthood, but some do. The survivors disperse into the stream, begin hunting, begin learning the water, and the cycle continues, generation after generation, as it has for millions of years. And that's where we'll pause for now. We've witnessed the drama of spawning season, the aggression, the kipes, the carefully chosen reds. We've watched eggs being laid and buried, waiting through the long winter. We've seen the miracle of hatching, the vulnerability of alevins, the critical moment when fry first rise to gulp air. It's a journey fraught with danger at every stage, yet somehow enough survive, enough make it through. Life persists. Rest now if you need to. We have more to explore, but there's no hurry. We're here for the long night, together, learning about trout, and perhaps about life itself, about persistence, about vulnerability, about the ancient rhythms that govern all living things. We'll continue when you're ready. Chapter 4. Here we are again, still exploring, still learning. By now, you might be wondering what it's actually like to be a trout. How does the world appear to them? What do they see, hear, smell, feel? How do they perceive the rushing water around them, the stones beneath, the sky above? These are questions worth pondering as we drift towards sleep. Because understanding how trout experience their world helps us understand not just trout, but perception itself, the way different creatures construct reality from the information available to them. So let's wade into the sensory world of the trout. Let's see through their eyes, feel through their lateral lines, smell through their nares. Let's experience the stream as they do. We'll start with vision, because sight is often our own dominant sense, and we naturally wonder, what can trout see? The answer is, quite a lot actually. Trout have exceptional underwater visual acuity, optimized for close-range clarity. Their eyes contain spherical lenses that provide perfect focusing and exceptional peripheral vision. This design allows them to spot prey and predators easily from nearly all angles, a crucial ability when you're both hunter and hunted, when threats can come from above, below, or either side. However, their eyes are generally set up to see things quite close. In freshwater, visibility is often less than 10 feet. The water carries sediment, algae, dissolved organic matter, all of which scatter and absorb light. So trout eyes evolved to excel at close range, where most of the important action happens anyway. Their field of vision is impressive. Trout have a 330-degree horizontal field of vision underwater, 330 degrees out of a possible 360. That means they have only two small blind spots, one directly in front of the nose and one directly behind the tail. Everywhere else they can see. Try to sneak up on a trout from the side. It sees you. From below, it sees you. From above at an angle, it sees you. But there's more to vision than just seeing in all directions. There's also depth perception, the ability to judge distance accurately. And for that, you need binocular vision. Two eyes seeing the same thing from slightly different angles, the brain combining those images to calculate depth. Trout possess binocular vision, but only in a narrow cone directly in front and above them. Their eyes angle slightly toward the nose, creating a 165-degree arc overlap where both eyes can see simultaneously. This binocular field provides increased detail, depth perception, and focusing ability. But here's the interesting part. This binocular field primarily covers the area directly in front of and above the trout. It extends approximately 10 feet forward, but is only about 1 to 2 feet wide. It's a narrow cone, a focused beam of enhanced vision pointing forward and upward, exactly where food typically appears, drifting on the current or falling from above. Outside this narrow cone, trout rely on monocular peripheral vision. This peripheral vision detects movement brilliantly, but it lacks depth perception. It's more of an alarm system, something's moving over there, than a detailed analysis tool. And here's a fascinating behavioral detail. Trout will reposition themselves to use binocular vision before deciding whether to take a fly. Even if a trout detects a potential food item in its monocular peripheral vision, it will shift position to focus on the item with its binocular vision to determine if it's actually food. This is why you sometimes see a trout move sideways or forward slightly before striking. It's bringing the target into that narrow binocular cone for final inspection. The binocular cone of vision is where trout primarily search for food. This makes accurate casting into this narrow zone critical for fishing success. Cast to the side of a trout, and it might see your fly, but it's seeing it with monocular vision, without depth perception. Cast into that forward cone, and the trout can examine it with both eyes, judge its distance, decide whether it's worth eating. Interestingly, trout are essentially both nearsighted in their binocular field and farsighted in their monocular field. Up close and forward, they have excellent focus. Farther away to the sides, they're observing distant objects, but without the same clarity or depth judgment. Now, what about the world above the water? Trout spend their lives underwater, but much of their food comes from above. Insects landing on the surface, terrestrial creatures falling in. Can they see the world beyond the water's surface? Yes, but in a strange, distorted way. Trout can see approximately 160 degrees of the world above water compressed into a 97-degree cone. This happens because light rays entering water are bent, refracted at the surface. The bending is quite dramatic, about 48.5 degrees at the horizontal plane. What this means is that when a trout looks upward, it sees a circular window into the above-water world. Through this window, it can see an enormous swath of the landscape, 160 degrees, nearly half of the total possible view. But it's all compressed, squeezed into a smaller visual angle of 97 degrees. Outside this window, the surface acts as a mirror, reflecting the bottom of the stream back at the trout. The surface becomes opaque from below, a silvery barrier showing only reflections. But within that window, the trout can see birds, trees, clouds, anglers standing on the bank. Everything is there, just distorted by refraction, compressed into a narrower field of view than it would appear from above water. One more detail. Trout positioned deeper in the water have larger circular fields of vision than those in shallow water. The deeper the trout, the wider the window. Geometry dictates this. The angle of the cone extends further at its opening, the deeper the apex of the cone sits. So what are trout actually good at seeing? What do they notice? Trout eyes cannot distinguish intricate detail, but excel at detecting movement and silhouettes. They lack the anatomical features that allow humans to see fine detail. This means flies used for fishing don't need to be perfect replicas down to every tiny detail. What matters is correct shape, size, color, and natural movement. Trout see silhouettes of objects and detect movement exceptionally well, rather than intricate patterns. If something moves unnaturally, a dead drift that suddenly speeds up, a swimming motion that doesn't match any real creature, trout notice. but slight imperfections in the pattern of spots on an artificial fly. They likely don't register that level of detail. Their color vision is particularly tuned to blue and green wavelengths, which are most common in freshwater environments. Water absorbs red and orange wavelengths quickly. They don't penetrate far. But blue and green light travels much further through water, and trout eyes have evolved to be especially sensitive to these colors. In fact, trout can see in color, and are particularly sensitive to green and orange wavelengths. The retina of a trout's eye is rich in cones, the cells responsible for color vision in bright light. This allows trout to perceive various colors across the spectrum. They're especially tuned to green and orange light, the most common wavelengths in their freshwater world, the ones that penetrate best through their environment. There's one more peculiarity about trout vision worth mentioning. Trout eyes adapt slowly to changing light conditions, taking hours rather than seconds. Unlike human eyes, which adjust to bright or dim light in fractions of a second, trout eyes can take hours to fully adapt to changing conditions. Trout have large pupils that let in as much light as possible, and the iris will not expand or contract like human eyes during changing light. Their eyes are essentially set up to work in low light conditions, even during the day. This makes sense. They live underwater, where light is already reduced, and they need to function in the dimness of dawn and dusk, when many insects are active. But it means that rapid changes in light can leave trout temporarily at a disadvantage. A sudden bright light in darkness, or a sudden shadow in bright conditions, and they need time to adjust. Hours, potentially, for full adaptation. Let's shift now from vision to other chemical senses, to taste and smell. Here's something remarkable. Trout have taste buds distributed throughout their entire body, not just in their mouth. Fish actually have the highest number of taste buds recorded for vertebrate animals. The amount of neural tissue devoted to sensing taste approaches 20% of the entire brain mass in some fish species. 20%. Imagine devoting a fifth of your brain to taste. These taste buds appear as small pores with sensory cells connected to nerves. They're located on the lips, mouth, tongue, and gill rakers, as you might expect. But they're also scattered throughout the body surface. This allows trout to literally taste their environment as they swim, without putting anything in their mouth. They're swimming through a soup of chemical information, constantly sampling it through their skin, detecting dissolved substances, analyzing the water itself. It's a form of perception we can barely imagine because our taste buds are confined to our mouths, and we experience taste only when we eat. For a trout, taste is ambient, constant, environmental, and then there's smell, which for trout is exceptionally acute. Trout possess two specialized holes called nares, essentially nostrils, that allow them to detect minute traces of chemicals in the water. Their sense of smell is so developed that it enables them to track prey over long distances in murky water and at night, when vision is limited or useless. Research shows that fish can use smell to navigate back to their birthplace. This is how salmon and steelhead find their home streams after years in the ocean. They remember, or perhaps recognize, the specific chemical signature of the water where they were born. Each stream has its own unique blend of minerals, organic compounds, dissolved substances, And trout, with their acute sense of smell, can detect and identify these signatures. It's like each stream has its own scent, its own olfactory fingerprint, and trout, after years away, can follow that scent home like a thread leading back through the maze. Now let's talk about hearing and vibration, because sound travels very differently underwater than in air. Trout have excellent hearing through specialized organs. They don't have external ears like humans. No ear flaps, no visible openings. But they possess internal hearing organs, and they rely heavily on something called the lateral line system that detects sound vibrations transmitted through water. Sound travels 4.5 times faster through water than through air. This makes trout highly sensitive to noise, especially in calm, deep water, where sound transmission is clearest. A footfall on the bank, the scrape of a boot on rock, the splash of a careless wade. All of these transmit vibrations through the water that trout can detect from up to 12 meters away. That's about 40 feet. That's a considerable distance. This is why experienced anglers move slowly and carefully near streams, not just to avoid being seen, but to avoid being heard. Vibrations matter. Noise matters. The lateral line system deserves special attention because it's truly remarkable. Trout have a sophisticated lateral line system that functions as a sixth sense. The lateral line runs down each side of a trout and across its head, visible as a faint line of scales with tiny pores in them. Inside, the system consists of tiny sensors called neuromasts that detect even the faintest changes in water movement and pressure. These neuromasts are like microscopic accelerometers, constantly monitoring the flow of water around the fish's body. Fish use their lateral line to locate prey, detecting the vibrations of a swimming minnow or struggling insect. They use it to escape from predators, feeling the pressure wave of an approaching threat before they even see it. And they use it to form cohesive schooling patterns, maintaining spacing and coordination with other fish through the subtle pressure changes each fish creates as it swims. It's a sense we don't have, can't really imagine having. The closest analogy might be feeling air currents on your skin, but vastly more sensitive and informative. For a trout, the water is constantly speaking, constantly providing information through pressure and flow. And the lateral line is how they listen. There's one more sensor worth mentioning, one that scientists only recently understood. The adipose fin, that small, fleshy fin located between the dorsal fin and the tail, was long thought to be vestigial, left over from evolution, serving no real purpose. In fact, it's often clipped off hatchery fish as an identification mark. But recent research reveals the adipose fin is highly innervated and functions as a mechanosensor that detects fluid flow. The fin encodes information on both movement and position of the fin membrane, functioning as what researchers call a precaudal flow sensor, a sensor just before the tail that helps trout detect and respond to complex water flows. This helps trout maintain position in turbulent water, adjusting constantly to swirls and eddies and chaotic flows. And studies have shown that removing the adipose fin reduces swimming efficiency in juvenile rainbow trout. It's not vestigial at all. It's a working sensor, providing constant feedback about the water rushing past the tail. Finally, let's talk about something truly strange and wonderful: magnetoreception. Rainbow trout possess magnetoreception abilities and can be trained to respond to magnetic field changes. Scientists have successfully trained trout using operant conditioning to respond to changes in both vertical and horizontal components of magnetic fields. How do they detect magnetic fields? Researchers have found magnetite in the trout's nose, closely associated with a nerve that responds to magnetic stimuli. Magnetite is a naturally magnetic mineral, essentially tiny biological magnets. These magnetite crystals are single domain, about 50 nanometers in diameter, serving as permanent magnets embedded in the fish's tissue. When the magnetic field shifts, these tiny magnets shift too, stimulating the associated nerve, sending signals to the brain, and the conditioned responses to magnetic direction changes persist in darkness, suggesting compass information is conveyed through a light-independent pathway. The trout doesn't need to see to sense magnetic fields. It's a separate sense entirely. This might help explain how trout navigate, how they orient themselves in their environment, how migrating fish find their way across vast distances. They're reading the Earth's magnetic field, using it as a map and compass combined, sensing variations and patterns we can barely detect with our most sophisticated instruments. Imagine that. Imagine sensing the invisible magnetic field that wraps around our planet, using it to know which way is north, which way is home. It's a sense so alien to human experience that we struggle even to conceptualize it. But for trout, it might be as natural and constant as our own sense of up and down, our internal awareness of gravity. And so we begin to understand. A trout experiences a world rich with information we cannot perceive. They taste the water itself. They hear and feel vibrations through their lateral line. They see in all directions, peer through a compressed window into our world above the water. They smell chemical traces and follow scent trails. They sense magnetic fields and orient themselves to the invisible lines of force that thread through the earth. They are not simple creatures. They are sophisticated perceivers, navigating a complex environment with an array of senses fine-tuned by millions of years of evolution. And that's where we'll pause for now. We've explored the sensory world of trout, walked through their perception, tried to imagine what it's like to be a creature so different from ourselves, yet so beautifully adapted to its world. Rest your mind on that thought. Let it drift. There's more to come. But for now, just breathe and imagine. Imagine being a trout, suspended in current, every sense alive and attuned to the flowing world around you. We'll continue soon. Chapter 5. We're moving deeper now into the life of the trout, past their physical form and their senses, into behavior itself. How do trout interact with each other? When do they feed? How do their bodies respond to the changing seasons, to the warming and cooling of the water that is their entire world? These are quieter questions, perhaps, but no less fascinating. So let's continue our gentle exploration. Let your breathing slow. Let your mind wander along with us through these cold water rhythms. Let's start with a question. Are trout social creatures? Do they swim in schools like sardines or minnows, moving in coordinated masses through the water? The answer is more nuanced than a simple yes or no. Trout do not naturally school, but may form loose aggregations based on social dynamics. While many fish species exhibit true schooling behavior, swimming in the same direction in a coordinated manner, moving as one organism, trout are not obligate schoolers. They don't need to school. They're not built for it, not programmed for it. But that doesn't mean they're completely solitary either. Rainbow trout do form social hierarchies and dominant structures. Aggression and agonistic interactions, conflicts, confrontations, displays of dominance are common, especially around feeding areas, where food is concentrated, where multiple trout want access to the same productive spot. Hierarchies develop. Larger, more aggressive fish establish dominance. Smaller or more timid fish learn their place in the social order. Interestingly, wild-caught trout tend to eat more and sooner when in visual contact with another fish than in isolation. This suggests some social facilitation of feeding behavior. Seeing another trout eat seems to stimulate appetite, to trigger feeding behavior. Perhaps it's competition. Get food now before the other fish takes it all. Perhaps it's simply information. If another trout is feeding, that means food is available and safe to pursue. This social dimension of trout life runs deeper than you might expect. Social interactions and experience significantly influence trout feeding and competitive behavior. Studies show that social interactions among trout play a greater role in experimental outcomes than the actual treatment effects researchers are testing. The presence of other fish, the establishment of dominance hierarchies through aggressive interactions, changes everything. The rate of agonistic interactions increases when feeding locations are limited. Makes sense, doesn't it? Put multiple trout in a tank with only one food dispenser, and they'll fight over access. But spread food out, give everyone a chance, and the aggression decreases. Swimming speed increases sharply before meal times in competitive environments. Trout anticipate feeding time, become more active, more alert, more ready to compete. It's not just stimulus response. There's anticipation, preparation, strategy. Rainbow trout exhibit higher activity levels and aggression compared to brown trout. This might reflect different stress responses, or it might be a result of domestication effects. Rainbow trout have been raised in hatcheries for many generations, while brown trout are often more recent from wild stock. Domestication changes behavior, sometimes in subtle ways, sometimes in obvious ones. Speaking of activity levels, let's talk about daily rhythms. Do trout have internal clocks? Do they have preferred times of day for different activities? Yes, they do. Rainbow trout exhibit circadian rhythms and distinct day-night activity patterns. Studies demonstrate circadian rhythms of demand feeding activity and locomotor activity in rainbow trout. Laboratory activity patterns in wild brown trout parr, that's young brown trout, associate with circadian activity, growth, and mortality in their natural environment. Here's something fascinating. Research shows that inactive trout in laboratory settings become more active at night. This suggests individual fish have what we might call early bird and night owl activity patterns. Some trout are more active during the day. Others prefer the night. Just like humans have chronotypes, some of us are morning people, some are evening people. Trout seem to have individual preferences too. Daily changes in light and dark periods influence physiological processes, including feeding, resting, and locomotor activity. The rhythm of day and night, the cycle of light and darkness, entrains these internal patterns. It's one of the fundamental rhythms of life on Earth, and trout, like most organisms, are attuned to it. There's another interesting discovery about feeding rhythms. Photoperiod independent diurnal feeding can improve growth performance by inducing food anticipatory activity. That's a mouthful of scientific language, so let's break it down. Rainbow trout fed on a regular daily schedule exhibit significant rhythms in feeding-related genes, even under constant light conditions. Even when you keep the lights on all the time, eliminating the day-night cycle, trout still develop feeding rhythms if you feed them at the same time each day. Their bodies anticipate the meal, prepare for it at the genetic level. This food anticipatory activity improves growth and feed utilization in juvenile rainbow trout. Anticipating food means being ready to eat when food arrives, means digesting it more efficiently, extracting more energy from it. It's a performance advantage. Temporal behavioral patterns show that stationary swimming, holding position in current, is less frequent in the morning and increases by midday and afternoon. Perhaps they're more actively hunting in the morning, moving around more. By afternoon, they've settled into holding lies, conserving energy while still watching for food. Now let's shift to what trout actually eat, and some of their more surprising feeding behaviors. Here's something that might shock you. Trout are cannibalistic and will consume smaller members of their own species. Like many other fish species, trout are cannibals. They will eat smaller trout without hesitation. This behavior is particularly common when food is scarce or when smaller trout are vulnerable, perhaps injured, perhaps trapped in a small pool. It's remarkable how even small trout can eat another fish almost as large as themselves. Their mouths are elastic, their throats expandable. They can swallow prey that seems impossibly large. A 6-inch trout can eat a 4-inch trout. It takes effort, takes time to work the prey down, but they manage it. It seems brutal, perhaps, by our standards. But in the trout's world, it's just efficiency. Protein is protein. Calories are calories, and a smaller trout represents a substantial meal worth far more energy than a dozen mayflies. And trout don't just eat fish. Large brown trout are known to prey on rodents and mice. When small mice or other rodents fall into streams, crossing on a log perhaps, or simply misstepping at the water's edge, brown trout will emerge from the depths to devour them. This behavior is well documented among anglers, some of whom fish with mouse imitations, swimming them across the surface to trigger strikes from large, predatory brown trout. It demonstrates the opportunistic and aggressive feeding nature of these fish. They're not picky. If it's meat and it's available and it fits in their mouth, it's food. Feeding behavior also changes dramatically with the time of day. Trout are highly active at night and adopt different feeding strategies after dark. Big trout feed differently at night compared to daytime. They move from deep holes, their daytime refuges, into shallow water, sometimes as shallow as 6 inches, to hunt for baitfish, crayfish, and other prey. Brown trout are the most likely species to stop feeding during the day due to angling pressure and become nocturnal feeders. If a stream sees heavy fishing pressure, if trout learn to associate daylight with danger, they simply shift their schedule. They become night hunters, emerging only when humans are gone. The best fishing for these nocturnal trout typically occurs during the first 1 to 1.5 hour window after darkness falls. That's the prime time, the magic hour when trout have emerged from hiding, but haven't yet satisfied their hunger. After that, they may continue feeding, but the intensity decreases. Let's talk now about temperature, because temperature governs so much of a trout's life. Trout are cold-blooded. Their body temperature matches the water temperature, and water temperature dictates their metabolism, their activity level, their entire pace of life. The optimal temperature threshold for increased trout activity is around 40 degrees Fahrenheit. Water temperatures approaching 40 degrees and beyond represent a magic number for trout activity. As water warms to this temperature, trout metabolism increases. Aquatic insects become more active, hatching in greater numbers, and feeding behavior intensifies. Below this temperature, both trout and their prey remain dormant or grow very slowly. Everything slows down. It's not that life stops, it just downshifts into a lower gear, conserving energy, waiting for better conditions. This leads us to winter, to the coldest months, when streams ice over or flow barely above freezing. What do trout do in winter? Trout exhibit winter dormancy behavior with dramatically reduced activity and feeding. During winter, trout enter a dormant or lethargic state characterized by inactivity, fasting, and low metabolic rates as water temperatures drop. Their metabolism slows down significantly in cold water, making them less aggressive feeders. They don't hibernate exactly. They're still conscious, still aware, still breathing. But they move very little. They find a protected lie, behind a boulder, in a deep pool, somewhere out of the main current, and they hold there. Days pass, weeks pass. They barely eat. Their bodies run on minimal energy, burning through fat reserves accumulated during the abundance of summer and fall. Studies show that activity reductions and the passive physicochemical slowing of metabolism due to cold, rather than active metabolic rate depression, are the primary energy-saving mechanisms in overwintering trout. In other words, trout don't actively suppress their metabolism. They simply slow down because cold water inherently slows all chemical reactions, all biological processes. It's passive conservation. The cold does the work. The trout just endures, waiting for spring, for warmth, for the return of abundant food and the energy to pursue it. And when spring comes, when water temperatures climb back toward that magic 40-degree threshold, everything changes. Metabolism kicks back into higher gear. Insects begin hatching. Trout emerge from their winter refuges, ravenous, ready to feed aggressively and rebuild the body mass lost during the lean months. It's a cycle as old as seasons themselves. Feast and famine, activity and rest, growth and dormancy, and trout have evolved to navigate this cycle with remarkable efficiency, timing their lives to the rhythm of cold and warm, abundance and scarcity. Imagine living that way. Imagine your entire metabolism, your energy level, your appetite, all controlled not by internal will, but by the temperature of your environment. When it's cold, you slow down whether you want to or not. When it warms, you speed up, become hungry, become active. For trout, there's no fighting it. The water temperature is what it is. And the trout adjusts, always adjusting, always matching its internal state to external conditions. It's a different way of existing, a different relationship with the world. Not worse or better than our warm-blooded constancy, just different. And in its own way, perfectly suited to life in cold, flowing water, where temperatures fluctuate with the seasons. And that's where we'll rest for now. We've explored the social world of trout, their hierarchies, their conflicts, their loose aggregations. We've seen their daily rhythms, their circadian patterns, their anticipation of meals. We've discovered their surprising diet, cannibalistic, opportunistic, willing to eat mice and smaller trout alike. And we've understood how temperature governs their lives, speeding them up or slowing them down, dictating the very pace of their existence. The night continues, the exploration continues. But for now, let your thoughts drift like a trout in slow current, barely moving, conserving energy, waiting. We'll be here when you're ready to continue. Chapter 6. Still here with us? Or perhaps you've drifted away and come back, slipping between wakefulness and sleep, like a trout moving between pools. Either way, welcome. We're continuing our journey now into the internal workings of the trout, the hidden processes, the chemistry and mechanics that keep these fish alive, that transform food into energy, that power muscles through cold water. These are intimate details, the kind that happen invisibly, constantly, beneath scales and skin. So settle in. Let your mind follow along, or let it wander. There's no test at the end. Just information, flowing like water, washing over you gently. Let's begin inside the trout's stomach, in the dark chamber where food goes to be broken down and transformed into something the body can use. The trout's stomach pH drops as low as 2.7 during active digestion, but recovers quickly. 2.7 is quite acidic. Not as acidic as a rat's stomach, which reaches pH 1.3 and sustains it for 3 hours, but still impressively acidic. For reference, lemon juice has a pH around 2, and battery acid is close to 0. So a trout's stomach during digestion is approaching lemon juice acidity. But here's the interesting part. This acidity is only transiently sustained for about 1 hour. The stomach drops to pH 2.7, does its work, then recovers back toward neutral. It's a brief but intense acidification. The stomach achieves this by secreting chloride ions at a rate of 1.1 millimoles per kilogram per hour. If you calculate the theoretical pH of the secreted fluid itself, it would be pH 0.6, extremely acidic, essentially hydrochloric acid, at a concentration of 240 millimoles per liter. But this gets diluted by the stomach contents, by the water secreted during digestion, so the actual stomach pH doesn't reach that extreme level, This acidity serves crucial functions. The stomach converts pepsinogen to pepsin rapidly at pH 2.0 to 4.0. Pepsin is the enzyme that breaks down proteins, chopping long protein chains into smaller pieces that can be absorbed in the intestine. And dietary acidification can enhance phosphorus digestibility and protein digestion, making nutrients more available to the fish. Now, here's something you might not expect. The stomach of a trout undergoes significant water secretion during digestion. Large additions of water to stomach chyme, that's the semi-liquid mass of partly digested food, occur within the first 2 hours following feeding. About 7.1 milliliters per kilogram of body weight in those first 2 hours, amounting to approximately 16 milliliters per kilogram over the first 12 hours. That's a lot of water. The water content in the stomach increases twofold from food to stomach contents within 2 hours. The stomach is actively secreting water into itself, diluting the food, creating a liquid environment for digestive enzymes to work. And when this watery chyme enters the anterior intestine, the first part of the intestine, a further large water secretion occurs, about 3.5 milliliters per kilogram. More dilution, more fluid, creating the conditions for nutrient absorption downstream. The size of the stomach itself varies quite a bit. Stomach capacity in trout varies with fish size and season. Brown trout stomach capacity ranges from 0.02 cubic centimeters in a small trout, 170 millimeters fork length, about 6.5 inches, all the way up to 0.93 cubic centimeters in a larger trout at 340 millimeters, about 13.5 inches. And stomach capacity appears to change between summer and winter seasons. Winter capacities are generally smaller than summer measurements. Perhaps because trout eat less in winter, their stomachs atrophy slightly, shrink to match the reduced workload. Or perhaps smaller stomachs in winter help conserve energy, reducing the metabolic cost of maintaining unnecessary tissue. The amount of food in the stomach at the beginning of digestion has the most pronounced effect on digestion rate. A full stomach digests faster than a partly full stomach. Perhaps the mechanical distension stimulates secretions. Perhaps it's simply that with more food present, digestive processes ramp up to handle the load. And in some trout populations, stomach changes can be truly dramatic. Some trout species can dramatically expand their digestive tract during feeding binges. Certain Alaskan trout species exhibit remarkable gut plasticity. Their stomachs and intestines double to quadrupling in size during month-long eating binges each August. This adaptation allows them to maximize nutrient intake during periods of abundant food availability, particularly during salmon spawning runs. When millions of salmon return to spawn and die, when their eggs drift downstream and their bodies decay and provide nutrients, the trout gorge themselves. Their digestive tracts expand to handle the feast, processing enormous amounts of food, storing away energy for the lean months to come. It's an extraordinary adaptation. Organs that can double or quadruple in size, then shrink back down when the abundance passes. Imagine if our stomachs could do that, expanding during holiday feasts and contracting during January diets. Let's talk now about what happens after digestion, about how trout process energy at the cellular level, particularly after intense activity. Trout lactate metabolism relies heavily on in situ, muscle glycogen resynthesis, rather than liver conversion. That's a technical statement, so let's break it down. When muscles work hard, when a trout sprints to escape a predator or fights against a strong current, the muscles burn through their stored glycogen, their sugar reserves. This produces lactate as a byproduct, which accumulates in the muscle and blood. Lactate buildup is what causes that burning sensation in our own muscles during intense exercise. The question is, what happens to that lactate during recovery? In mammals, much of it goes to the liver, which converts it back to glucose through a process called gluconeogenesis, then ships that glucose back to the muscles. This is called the Cori cycle. but trout do it differently. After exhaustive exercise, blood lactate is cleared primarily through direct uptake by muscle for glycogen resynthesis. The muscles themselves take the lactate and convert it back into glycogen, storing it locally for the next bout of activity. The liver is less involved. In fact, studies show that when trout are functionally hepatectomized, when their liver function is blocked, muscle metabolic recovery is actually faster than in control fish. This suggests that glycogen resynthesis in trout muscle may normally be retarded because the liver is competing for lactate, using it for its own processes rather than letting the muscles reclaim it directly. It's a different metabolic strategy than mammals use. Not better or worse, just different. Evolved for the specific demands of being a cold water fish. The liver still plays crucial roles, of course. The liver is the primary organ for lipid metabolism and plays a central role in trout metabolic homeostasis. Similar to mammals, lipogenesis, the creation of fats, triglyceride accumulation, and metabolic homeostasis occur essentially in the liver of rainbow trout. The liver regulates glucose and lipid metabolism through insulin signaling and something called the TOR pathway, a complex signaling network that responds to nutrient availability and controls growth and metabolism. Different genes get turned on or off based on fat content in the diet, with genes like L-FABA-P, adiponectin, and PPR being differentially expressed. Interestingly, social status also affects liver lipid metabolism. Subordinate trout, those low in the dominance hierarchy, show altered liver function compared to dominant individuals. Stress from social subordination changes metabolism at the organ level. It's a reminder that behavior and physiology are not separate. They're intertwined, each affecting the other. Let's talk now about the trout's heart and cardiovascular system, particularly during intense activity. The coronary circulation is critical for trout cardiac performance and metabolism. The coronary circulation is the blood supply to the heart muscle itself. In trout as in us, the heart needs its own blood supply to function. It's not enough that blood passes through the heart chambers. The thick muscular walls need their own dedicated vessels, bringing oxygen and nutrients. Studies where rainbow trout had their coronary artery ligated, blocked, showed dramatic effects. These trout exhibited a 29% reduction in aerobic scope. Aerobic scope is the difference between resting metabolic rate and maximum metabolic rate. Essentially, how much extra performance capacity the fish has for intense activity. This reduction came from a 19% reduction in maximum metabolic rate. With impaired blood supply to the heart muscle, the heart couldn't pump as effectively during maximum exertion. The coronary system delivers fully oxygenated arterial blood to the outer compact myocardium, the dense muscle tissue of the heart wall, which is essential during metabolically demanding situations like spawning migrations and environmental warming. Coronary ligated trout showed elevated resting heart rates to compensate for impaired stroke volume. Resting heart rate went from 41.9 beats per minute up to 53.9 beats per minute. The heart was beating faster to compensate for moving less blood with each beat, like revving an engine higher to maintain speed when power output is reduced. It demonstrates just how finely tuned the cardiovascular system is, how dependent performance is on adequate blood supply to the heart itself. Finally, let's talk about efficiency. Specifically, how efficiently trout convert food into body mass under optimal conditions. Rainbow trout achieve exceptional feed conversion ratios under optimal aquaculture conditions. Feed conversion ratio is simple. How many pounds of food does it take to produce 1 pound of fish? In recirculating aquaculture systems, highly controlled environments where water quality, temperature, and feeding are all optimized, rainbow trout typically achieve feed conversion rates of 1.0 or less for fish smaller than 100 grams. That means 1 kilogram of food produces 1 kilogram of fish. That's exceptional efficiency. For fish between 100 grams and 1 kilogram, the ratio is 1.0 to 1.3, and for larger fish, it's 1.3 to 1.5. So even in the worst case among these optimal conditions, it takes only 1.5 pounds of food to produce 1 pound of trout. For comparison, beef cattle typically have feed conversion ratios around 6 or 7, 6 to 7 pounds of feed for 1 pound of beef. Pigs are around 3. Chickens are around 2. So trout, at 1 to 1.5, are remarkably efficient converters of feed into flesh. Some aquaculture operations routinely produce 900 gram to 1.4 kilogram fish. That's roughly 2 to 3 pounds, within 12 months post-hatch. From egg to market size in a year. That's fast growth, testament to good conditions and good genetics. And genetics matter. Genetic improvements in rainbow trout can reduce feed costs and nutrient loading by 18.3% compared to base populations. Selective breeding for growth rate, feed efficiency, and disease resistance produces fish that simply perform better. They grow faster on less food, produce less waste, survive better. It's a reminder that evolution doesn't stop in the wild. Humans conducting selective breeding are just evolution happening faster, directed by human preferences rather than natural selection. The result is fish increasingly well adapted to aquaculture conditions, just as wild trout are adapted to their stream conditions. Different pressures, different adaptations, but the underlying mechanisms, mutation, selection, reproduction, remain the same, and that's where we'll rest for now. We've journeyed through the trout's digestive system, watched acid dissolve food, and water dilute the mixture. We've seen how muscles handle lactate, how livers process fats, how hearts pump blood to themselves. And we've marveled at the efficiency of these fish when conditions are right. How effectively they transform food into flesh, energy into growth. The inner workings of a trout are complex, elegant, refined by millions of years of evolution, and in some cases, by decades of selective breeding. Every system interlocked, every process optimized for survival in cold water. Let that complexity wash over you. Let it fade into background knowledge, the kind you know but don't need to actively think about. Like your own heartbeat, your own digestion, happening constantly without conscious attention. Rest now. We'll continue when you're ready. Chapter 7. We're back now, continuing our exploration through the night. If you've been drifting in and out of consciousness, that's perfectly fine. That's exactly what this is for. A gentle journey that doesn't demand your full attention, that welcomes you whether you're awake or halfway to dreams. In this part of our story, we're going to talk about the water itself, the medium in which trout live, the substance that defines every aspect of their existence. Water temperature, water chemistry, dissolved oxygen. These aren't just environmental factors for a trout. They're everything. They determine whether a trout can live in a stream at all, whether it thrives or merely survives. So breathe slowly. Let the words flow over you like cool water. And let's continue. Let's start with the most fundamental requirement. Trout prefer cold, well-oxygenated water. All trout prefer cold, clear, and well-oxygenated freshwater environments. That's their niche, their preferred habitat, the conditions under which they evolved. However, not all trout species are equally demanding. Brown trout are more tolerant of warmer temperatures and higher turbidity, cloudiness, than other trout species. This gives them a competitive advantage in marginal habitats where other trout struggle. A stream that's too warm for brook trout or cutthroat trout might still support a healthy population of brown trout. They're the generalists of the trout world, the ones that can make do with less than perfect conditions. But even brown trout need certain minimums to survive, and oxygen is perhaps the most critical. Trout require high levels of dissolved oxygen to survive and thrive. Brown trout need dissolved oxygen levels of 9 milligrams per liter or higher for a healthy population. 6 milligrams per liter is the short-term lower boundary. They can survive at this level for a while, but they're stressed, not thriving. Below 3 milligrams per liter is lethal for brown trout. They asphyxiate from lack of oxygen. Their gills simply can't extract enough oxygen from water that depleted. It's like trying to breathe at the top of Mount Everest. You might survive briefly, but you can't sustain life there. Rainbow trout ideally need dissolved oxygen between 7 and 9 milligrams per liter. Concentrations below 5 milligrams per liter cause stress. The fish become lethargic, lose appetite, become vulnerable to disease. It's not immediately lethal, but it's not sustainable either. And for eggs and developing embryos, oxygen requirements are even higher. Trout and salmon eggs require at least 11 milligrams per liter for proper hatching. They will die in large numbers when levels fall below 6 milligrams per liter. Eggs can't move to better water. They're stuck where they were laid, entirely dependent on the water flowing through the gravel, maintaining adequate oxygen levels. This is why siltation is so damaging to trout reproduction. Silt fills the spaces between gravel, reducing water flow through the red. Reduced flow means reduced oxygen delivery to the eggs, and eggs that don't get enough oxygen die, sometimes by the thousands. Now let's talk about temperature, because temperature and oxygen are intimately connected. Cold water holds more dissolved oxygen than warm water. As water warms, oxygen solubility decreases, so warm water is a double threat to trout. It's physiologically stressful in itself, and it carries less oxygen. Trout have specific thermal tolerance ranges that vary by species and exposure time. For brook trout and brown trout, the 7-day upper tolerance limit is 23.3 degrees Celsius for mean temperature and 25.4 degrees Celsius for maximum temperature. Convert those to Fahrenheit, and you get 74 degrees and 78 degrees, respectively. Those are hard limits. Sustained exposure to temperatures above those thresholds is lethal. The fish will die, not immediately perhaps, but within days. Prime feeding water temperatures for trout are between 45 and 65 degrees Fahrenheit. That's when they're most active, most aggressive, most willing to expend energy hunting, and fishing in water over 67 degrees poses a risk to trout health. Even if you release the fish, the stress of being caught in warm water, the fight, the handling, the time out of water, can be enough to kill it hours or days later. This is why ethical anglers check water temperature and stop fishing when it gets too warm. The fish might still bite, but they're already physiologically stressed, and adding the stress of capture pushes them over the edge. Brook trout, being the most cold-adapted species, have developed a particular behavior in response to warming summer temperatures. Brook trout undertake dramatic upstream migrations in search of cold water during summer. Brook trout residing in larger streams exhibit high movement rates in summer, with some individuals moving 100 to 150 meters per day and traveling up to 2.6 kilometers upstream over a 65-day period. These movements are significantly related to maximum water temperature and distance from cold water sources. As water warms, brook trout move. They search for springs, for tributaries fed by snowmelt, for any source of cold water. Movement rates increase as fish get farther from cold water. They're actively searching, sometimes traveling kilometers to find refuge. It's survival behavior, driven by physiological necessity. In warm water, a brook trout is slowly dying. So it moves, searching, until it finds cold water or perishes trying. Beyond temperature and oxygen, there's another water chemistry variable that matters greatly to trout: pH, the measure of acidity or alkalinity. Trout prefer alkaline water with pH levels between 7.0 and 9.0. Cutthroat, rainbow, and brown trout favor alkalinity levels in this range and react negatively to pH levels below 6.0. Acidic water is physiologically stressful, interfering with ion regulation, gill function, reproduction. However, brook trout are notably more acid tolerant. They can survive and even reproduce successfully in water with pH as low as 4.5, though they prefer a range of 5.0 to 7.5. This acid tolerance is part of why brook trout persist in some Appalachian streams affected by acid rain, streams where other trout species have disappeared. Waters with higher alkalinity typically produce larger trout. This is because alkalinity correlates with nutrient availability. More alkaline water tends to support more aquatic invertebrates, more plant growth, more food for trout. And more food means larger, healthier fish. But the pH sensitivity of trout goes deeper than just preference. At the cellular level, pH affects blood chemistry directly. Trout red blood cell stability is highly sensitive to pH changes in their environment. Research shows that trout red blood cells undergo rapid hemolysis, cell rupture, at pH levels below 7.2. At pH 6.8, 50% hemolysis occurs within 4 to 5 days. At pH 6.4, hemolysis begins within just 2 days. The red blood cells are literally falling apart, rupturing, spilling their contents into the blood plasma. Higher pH levels, 7.6 to 8.0, significantly stabilize red blood cells. The presence of glucose at pH 8.0 provides additional protection. This pH sensitivity correlates with lipid oxidation of the red blood cell membrane and hyamin release from hemoglobin. Acidic conditions damage the cell membrane chemically, leading to rupture. Imagine trying to survive while your blood cells are disintegrating. It's no wonder trout avoid acidic water when they can. Now let's talk about salt. Most trout are freshwater fish, but some species, steelhead, sea-run brown trout, migrate to the ocean. How do they handle the transition from freshwater to saltwater? Rainbow trout gills undergo dramatic remodeling when transitioning between freshwater and saltwater. This remodeling is triggered by changes in internal salt levels. Dietary salt loading alone, without a change in external salinity, can induce elements of the seawater gill phenotype in freshwater rainbow trout. The gills upregulate ion transport genes, specialized proteins that pump ions in or out of the body. Chloride cell accessory cell complexes appear, structures normally restricted to seawater fish. This indicates that internal salt sensing is a critical cue promoting gill remodeling during migration. The fish's body detects rising internal salt levels and begins preparing for the ocean before it even gets there. Freshwater trout maintain internal salt concentrations 1/4 to 1/3 of seawater salinity. In freshwater, this means constantly preventing ion loss. Water flows into the fish through osmosis, diluting body fluids, so the gills must actively retain salts. In seawater, the problem reverses. Salts flow in, water flows out, so the gills must actively excrete salts and conserve water. It requires constant physiological adjustments, constant active regulation. It's energetically expensive, which is why not all trout can do it well. Brook trout, for instance, have limited saltwater tolerance compared to other salmonids. Brook trout 16 to 20 centimeters long have only partial ability to regulate plasma ions in 32 parts per 1,000 seawater. That's full-strength ocean water. Their plasma sodium, chloride, and osmolarity increase again after 21 days, with continuing mortalities throughout this period. Their seawater survival is limited by size, age, and photoperiod, day length, which triggers physiological preparations. Young brook trout simply can't osmoregulate effectively in salt water. Salmon and sea trout 11s, newly hatched fish, appear to be truly freshwater forms with no active osmoregulatory powers at any developmental stage. They must grow and develop before they can handle salt water. Finally, let's talk about the other temperature extreme, cold. We've discussed how trout struggle in warm water. But what about extremely cold water? Water near freezing? Most trout don't have special adaptations for extreme cold beyond their general cold water physiology. But it's worth noting that while trout do not possess antifreeze proteins like polar fish, some polar species have extraordinary capabilities that put trout to shame. Some polar fish, like the winter flounders, produce hyperactive antifreeze proteins, AFPS, that provide over 2 degrees Celsius of thermal hysteresis protection. That's more than double previous measurements. These proteins work in a remarkable way, non-colligatively, at concentrations 1/300th to 1/500th of other dissolved solutes. They bind directly to ice crystals to prevent their growth. The fish's blood can supercool below freezing without forming ice crystals that would rupture cells and kill the fish. The maximum thermal hysteresis shown by fish antifreeze proteins, is approximately minus 3.5 degrees Celsius. A snailfish discovered off Greenland has the highest expression of antifreeze proteins ever observed in any fish species. It lives in water that should freeze solid, but the antifreeze proteins keep ice from forming in its body fluids. Trout don't have this adaptation. They live in cold water, yes, but not in water that cold. They avoid the extreme polar conditions where antifreeze proteins become necessary. But it's fascinating to know that some fish have evolved this capability, that life has found a way to survive even in water at the edge of freezing. And that brings us to the end of this section. We've explored the water itself, the oxygen content, the temperature, the pH, the salinity. We've seen how narrow the habitable zone is for trout, how specific their requirements are. Too warm and they die. Too little oxygen and they suffocate. Too acidic and their blood cells rupture. Too salty for some species and they can't regulate their internal chemistry. Trout are cold water specialists, finely tuned to a specific set of conditions. They're not generalists like carp or catfish, not survivors in marginal conditions. They're specialists, exquisitely adapted to cold, clean, well-oxygenated water. And in such water, they thrive. They grow, hunt, spawn, persist. Generation after generation, as long as the water remains cold and clean. Rest now on that thought. Imagine cold water, clear water, flowing endlessly over stone. Imagine the trout holding steady in the current, perfectly adapted, perfectly at home. We'll continue when you're ready. Chapter 8. We're moving now into darker territory, though no less important. No less part of the complete picture of what it means to be a trout. Because life is not just about thriving. It's also about surviving. About the threats that exist in every stream, the diseases that lurk, the predators that hunt, the pollutants that poison. This is the shadow side of the trout's existence. But don't worry, we'll move through it gently as we've moved through everything else. Let the information wash over you. Let your breathing stay slow and steady. Even uncomfortable truths can be contemplated peacefully, from a distance, in the safety of this quiet night. So let's continue. Let's look at what threatens trout, what kills them, what they must navigate and survive to persist in their cold water world. We'll begin with disease, and with one disease in particular that has devastated trout populations across the world. Whirling disease is a deadly parasitic infection affecting trout worldwide. It's caused by a microscopic parasite called Myxobolus cerebralis, a name that hints at what it does. It attacks the cerebralis, the cartilage tissue of a trout's head and spine. The effects can be dramatic and disturbing. Infected trout may exhibit whirling behavior, swimming in circles or spirals as if chasing their own tail, unable to swim straight. They develop blacktails, head deformities, twisted spines. Many die, especially when infected as juveniles, while their skeleton is still developing, still cartilage that will later ossify into bone. Rainbow trout are the most susceptible species. They're hit hardest by whirling disease, with mortality rates that can approach 100% in severely affected populations. Brook trout are next in susceptibility, also vulnerable, but slightly more resistant. Brown trout show only partial susceptibility, They can be infected, but they're less likely to develop severe symptoms or die from it. The parasite has a complex life cycle involving aquatic worms, tiny tubifex worms that live in the muddy sediments of streams. The parasite cycles between the worms and the fish, and neither can be infected without the other. But once established in a stream system, whirling disease is nearly impossible to eradicate. The spores can survive in moist environments for years, waiting for conditions to allow the life cycle to continue. And there's no known treatment, no medication, no cure. Infected fish either survive or they don't, depending on their species, their age at infection, the severity of the infection, and luck. Some trout populations have developed partial resistance through natural selection. The survivors breed, passing on whatever genetic factors allowed them to resist. And over generations, the population becomes more tolerant. But it's a slow process, and many populations were decimated before any resistance could develop. Now let's talk about pollution, about the toxic compounds that humans inadvertently or carelessly introduce into trout streams. Early life-stage rainbow trout are highly sensitive to toxic pollutants, and one in particular has emerged as a major threat: 6-PPD quinone. That's a tire rubber derivative, a chemical that forms when a common tire preservative called 6-PPD reacts with ozone in the air. When it rains, this chemical washes off roads into streams. Rainbow trout alevins, those newly hatched fish with yolk sacs we discussed earlier, exposed to 6-PPDQ from hatch, until 28 days post-hatch showed a median lethal dose of 0.56 micrograms per liter. That's an extraordinarily small concentration, less than 1 part per billion. And at that concentration, half the alevins died. For exogenously feeding fry, those that have absorbed their yolk sac and started eating, the 96-hour lethal concentration was 0.47 micrograms per liter. Even lower, even more toxic. Brook trout fry are also sensitive, with a 24-hour lethal concentration of 0.2 micrograms per liter. 0.2 of a microgram per liter. That's almost nothing, yet it's enough to kill half the fish in a day. Rainbow trout are among the most sensitive fish species, tested for other toxins too: copper, zinc, sulfate. They're canaries in the coal mine, extremely sensitive indicators of water quality. Trout and salmon suffer significant mortality below pH 5.5, making them highly sensitive indicators of water acidification as well. Their sensitivity is both a curse and a blessing. A curse because it means they're easily harmed by pollution. A blessing because their presence indicates clean water, and their absence serves as an early warning that something is wrong. Interestingly, the sensitivity to 6-PPDQ varies dramatically among salmonid species, and this variation tells us something important about how toxins work. Coho salmon are the most sensitive salmoniid to 6-PPDQ, but their close relatives, Chinook salmon, are about 800 times more tolerant based on lethal concentration studies. 800 times. That's an enormous difference for closely related species. The difference comes down to liver detoxification capabilities. More tolerant species show higher levels of metabolites produced when liver enzymes react with 6-PPDQ, creating less toxic transformational compounds. Their livers are better at breaking down the toxin into something harmless. In sensitive rainbow trout, 6-ppdq causes oxygenated hemoglobin, the form that carries oxygen, to decrease, while methemoglobin, a form that's chemically blocked from taking up oxygen, increases dramatically. The fish essentially suffocates, even though there's plenty of oxygen in the water. Their blood can't carry it. Tolerant species like Arctic char show no major circulatory changes. The toxin enters their body, their liver breaks it down, and they survive without significant harm. It's a reminder that toxicity is not universal. The same compound can be deadly to one species and relatively harmless to another, all because of differences in metabolic chemistry, in detoxification pathways, in the specific enzymes each species produces. Because trout are so sensitive to pollution, they serve an important role in environmental monitoring. Brown trout serve as excellent sentinel organisms for biomonitoring organic pollution. Wild brown trout show significant induction of cytochrome. P450 enzymes, when exposed to organic pollutants like polycyclic aromatic hydrocarbons, PAH, which are common industrial pollutants found in coal tar, petroleum products, even charred meat. The cytochrome P450 enzymes are part of the liver's detoxification system. When pollutants are present, these enzymes are upregulated. The body produces more of them to handle the toxic load. And this upregulation is measurable, quantifiable, with significant differences between contaminated rivers and reference rivers. The wide difference between basal and induced P451A levels in trout under natural field conditions makes them ideal biomonitors for assessing exposure to industrial organic pollutants. Scientists can catch trout, measure enzyme levels in their liver, and know immediately whether significant organic pollution is present, even at levels too low to detect by direct water sampling. The trout become living pollution detectors, integrating exposure over time, accumulating evidence of contamination in their tissues. Now let's shift from disease and pollution to something more primal. Predation. Trout face predation from a wide variety of birds and mammals. It's a long list of hunters, a rogues gallery of creatures that view trout as food. Common predators include great blue herons, those tall, patient stalkers wading in shallows. Common loons, those diving birds that pursue fish underwater with astonishing speed. American mergansers, ducks with serrated bills designed for gripping slippery fish. Belted kingfishers, those hovering diving birds that plunge into water from the air. American bitterns, secretive herons that hunt in marshy areas. And then the mammals, mink, sleek and vicious, hunting along stream banks and swimming after fish underwater. Otters, playful but deadly efficient predators. Water snakes, though less common in colder streams, still taking their share where they occur. The numbers are sobering. Great blue herons consume approximately 1.5 pounds of trout per day. Common loons eat about 2.4 pounds daily. Otters consume roughly 0.7 pounds per day. In some Michigan trout waters, predators take more trout annually than fishermen do. Birds, mammals, and reptiles account for up to 62% of brown trout annual mortality. 62%. That means predation is the dominant mortality factor, more significant than fishing, more significant than disease, more significant than any other single cause of death. For a trout, the world is full of things trying to eat it. The heron standing motionless in the shallows, the otter sliding through the water, the merganser diving from above. Every trout that survives to adulthood has dodged death dozens of times, perhaps hundreds of times. Every large trout is a survivor, lucky and skilled in equal measure. Finally, let's talk about natural mortality patterns. The broader picture of when and how trout die throughout their lives. Natural mortality patterns in stream-living brown trout follow distinct life stage phases with varying causes. Brown trout exhibit either 2-phase or 3-phase mortality patterns, depending on population and environmental conditions. Early life mortality is high. Eggs that don't hatch, 11s that die in the gravel, fry that are eaten or starve, or succumb to cold or flood. Then comes juvenile mortality, competition for territory, predation, disease. And finally, adult mortality, senescentha, spawning stress, predation by larger predators, harvest by anglers. The causes are varied. Mortality factors include intrinsic causes, lethal alleles, genetic defects that prove fatal, metabolic constraints, the inability to process food or oxygen efficiently, age itself, the gradual wearing out of biological systems, sex and reproduction, particularly for females that invest enormous energy in egg production and spawning. And then extrinsic factors, space and food availability, density-dependent mortality, where too many fish compete for too few resources, parasites, predation, which we've discussed, diseases, extreme temperatures, both high and low, oxygen depletion during warm summer nights or under ice, winter conditions, ice dams, anchor ice that forms on the stream bottom, floods from snowmelt. Harvest mortality, fishing, is highest for intermediate-sized trout. The smallest are too small to keep, protected by size limits. The largest are often wary, hard to catch, and sometimes released by anglers who want them to survive and breed. But the middle-sized fish, 8 to 14 inches perhaps, are vulnerable. Legal to keep, easy enough to catch, and often harvested. In heavily fished waters, harvest mortality can outweigh background mortality for most size ranges. More fish die on hooks than from all natural causes combined. But in lightly fished or catch-and-release waters, natural mortality dominates. Predators, disease, starvation, temperature stress, these take the majority. It's a complex picture. Trout die from many causes at all life stages. The miracle is not that trout die. Death is inevitable for every individual. But that enough survive to perpetuate the population, to spawn the next generation, to keep the species going. Every trout you see in a stream is a winner in life's lottery, a survivor of odds stacked heavily against it. From the thousands of eggs laid, only a handful survive to adulthood. From the handful of adults, only a few live long enough to become large, old, wise fish. And that makes every encounter with a trout something worth appreciating. You're seeing a survivor, a creature that has navigated disease and pollution, evaded predators, tolerated temperature extremes and oxygen depletions, and lived to hold steady in the current for another day. And that's where we'll rest for now. We've walked through the threats: disease, pollution, predation, natural mortality. It's not a cheerful catalog, but it's real. It's part of what makes survival an achievement, what makes each living trout remarkable. Close your eyes if they're not already closed. Breathe slowly. Think of a trout holding in clear water, alive despite everything, persistent, resilient. More to come, but no rush. Rest if you need to. We'll be here. Chapter 9. We're approaching the final stretches of our journey now, moving through the night together. If you're still awake, your dedication is admirable. If you're drifting, that's perfectly fine too. We're here either way, continuing our exploration of the trout. This time looking at the very blueprint of their existence, the genetic code that makes them what they are, and how humans have intervened in that code, sometimes for better, sometimes for worse. So let your mind settle, breathe slowly, and let's explore the deepest level of the trout. The chromosomes, the genes, the molecular instructions that build a fish from a single fertilized egg. Let's start with the most basic genetic facts. How many chromosomes does a trout have? The answer depends on which trout you're asking about. Rainbow trout have 30 chromosomes. Brown trout have 38 to 42 chromosomes. The number varies, which is itself interesting. And brook trout have 42 chromosomes. These aren't arbitrary numbers. Each chromosome carries thousands of genes, and the organization of those genes, the way they're packaged and expressed, determines everything about the fish. The rainbow trout genome contains approximately 46,585 annotated protein-coding genes, organized into 38 pairs of large duplicated regions distributed over those 30 chromosomes. Brown trout exhibit variable chromosome numbers, ranging from 38 to 42, due to high genetic diversity. Their genome spans 2.37 gigabases. That's 2.37 billion base pairs of DNA, and contains 43,935 protein-coding genes. Brook trout have 42 chromosomes and 56,058 genes in their genome. These are large genomes, complex genomes, befitting complex organisms, and there's a reason rainbow trout have so many genes. More than you might expect for a fish. The rainbow trout genome underwent whole genome duplication 100 million years ago. This was a relatively recent event in evolutionary terms. A whole genome duplication, meaning every single gene was suddenly present in duplicate. The entire genome doubled. This duplication event resulted in 48% of ancestral pre-duplication genes being retained as duplicated copies, called onologues, a whimsical scientific term honoring Susumu Ono, who first proposed that gene duplication drives evolution. The other 52% reverted to singletons. One copy was lost over time, leaving only one functional gene where there used to be two. The ancestral pre-duplication genome contained an estimated 31,476 genes. So roughly half of those genes are now present in duplicate, giving rainbow trout this expanded genome, this genetic flexibility that allows for specialization and adaptation. About 90% of the rainbow trout genome is composed of 88 pairs of collinear blocks of high-sequence similarity known as homologous chromosome regions. That's technical language for saying that much of the genome exists in two nearly identical copies, side by side, remnants of that ancient duplication. This genomic architecture has implications. Duplicate genes can evolve new functions, can specialize, can provide backup if one copy fails. It's genetic redundancy, but also genetic opportunity. Now let's talk about sex determination, about how trout become male or female, and how humans have learned to manipulate this process. Trout sex determination follows an XX-XY system. This is the same system humans use, though independently evolved. XX individuals are female, XY individuals are male. But here's where it gets interesting. Mutations can override normal development. Rainbow trout typically have female homogamity, XX females, XY males, but mutations in sex-determining genes can override this system. A mutation termed male can induce testicular development in expected XX individuals, causing sex reversal. You get a genetic female that develops as a functional male. Males can be artificially feminized through estrogen exposure. By treating young fish with female hormones during the critical period of sex determination, and breeding these feminized males, genetic males that look and function as females, produces YY supermales that sire 100% male offspring. No daughters, only sons, because they have no X chromosome to pass on. Sexual dimorphism, physical differences between males and females, becomes apparent by age 2, with males developing that hooked jaw we discussed earlier, the kype. Humans have also learned to manipulate the number of chromosome sets in trout, creating what are called triploid fish. Triploid trout are functionally sterile fish, with 3 sets of chromosomes instead of 2. Normal fish are diploid, 2 sets, but triploidy is induced by applying hydrostatic pressure or temperature shock to fertilized eggs shortly after fertilization. This treatment prevents the expulsion of the second polar body. Normally, eggs discard half their chromosomes during maturation, but the pressure or temperature shock stops this process. The result is retention of a 3rd chromosome set. The egg keeps the chromosomes it was supposed to discard, and when fertilized by a sperm with its normal single set, you get 3 sets total. Triploidy. This achieves 98 to 100% sterility rates in both males and females without any genetic modification. No gene editing, no transgenic manipulation. Just a physical treatment applied at the right moment during development. Female triploids are completely hormonally and functionally sterile. They never develop mature eggs, never experience spawning condition, never waste energy on reproduction. But interestingly, male triploids still produce hormones causing maturation changes, including flesh quality deterioration and development of secondary sex characteristics. They're sterile in the sense that they can't reproduce, but their bodies don't entirely know that. Why create sterile trout? There are several reasons. Triploid trout may live longer and grow larger than diploid trout. They're not subject to increased mortality associated with maturation and spawning. They don't exhaust themselves reproducing, so they survive better. After 3 years of age, triploid trout tend to grow larger than non-sterile trout because they don't expend energy on reproduction. This results in more bright fish, colorful, healthy-looking fish, being available to the fishery, and it reduces risks of genetic interactions between hatchery and wild fish. Since the stock trout can't successfully breed with wild populations, it's a management tool, controversial in some circles, embraced in others. Speaking of hatcheries, let's talk about what happens when trout are raised in captivity for generations. Hatchery environments can cause rapid domestication effects and reduced fitness in trout. Captive rearing leads to reductions in reproductive success, decreased egg size, altered gene expression patterns, and potential breakdown of co-adapted gene complexes. Sets of genes that work well together evolved over thousands of generations, but that fall apart when selection pressures change. Hatcheries may unintentionally select for different breeding behaviors, body shape, and coloration that reduce fitness in wild environments. For instance, in hatcheries, the most aggressive feeders do best. They get to the food first. But in the wild, excessive aggression might waste energy or expose fish to predators. In hatcheries, wariness of humans is a disadvantage. Wary fish don't feed well. But in the wild, wariness is survival. Offspring of first-generation hatchery, steelhead show measurable domestication effects. Physiological or behavioral traits selected for survival in hatchery conditions may be maladaptive in nature, and these effects can appear quickly within a single generation raised in captivity. The results in the wild are sobering. Stock trout have alarmingly low survival rates in the wild. Studies show that stock trout survival rates range from less than 5% to 14% by the end of the first year, even in catch-and-release waters where fishing mortality is minimal. A New Jersey study found that out of 75 spring-stocked rainbow trout, only one survived by summer's end, with birds being the primary predator. Mean annual mortality of stocked rainbow and brown trout exceeds 95%, with most dying within the first few months from predation, stress, and inability to adapt to wild conditions. They're not stupid fish or defective fish. They're just fish adapted to hatchery life, suddenly thrust into an environment they're not prepared for. They don't know where to hide. They don't recognize predators quickly enough. They're used to food appearing magically at regular intervals, and they die in enormous numbers. Yet, despite over a century of extensive stocking in many regions, something surprising has happened. Or rather, hasn't happened. Long-term hatchery stocking has resulted in surprisingly limited genetic introgression in most wild trout populations. Despite over a century of extensive stocking in some regions, most wild brook trout populations show limited to no evidence of hatchery introgression, with less than 5% hatchery ancestry. Hatchery stocks remain genetically distinct from wild populations. Only locations using local strains for supplementation, hatchery fish derived from the local wild population, show substantial hatchery-derived fish. The amount of hatchery stocking within a watershed does not necessarily predict the level of genetic introgression. Why? Probably because hatchery fish are so maladapted to the wild that they rarely survive long enough to reproduce. They die before spawning. The genetic barrier isn't inability to interbreed. It's inability to survive. Natural selection is brutal and efficient. However, when different species interbreed, the genetic consequences can be more persistent. Backcross hybrids between trout species can perpetuate genetic introgression across generations. When fertile F1 hybrids, first-generation crosses between species, backcross with parental species, introgressive hybridization can alter the genetic structure of populations and introduce maladaptive alleles from one species into another. Backcrossed individuals have been found in drainages lacking F1 hybrids and in populations previously thought to contain only a single species. Rainbow and cutthroat trout backcross hybrids typically exhibit mitochondrial DNA from the recurrent parent. indicating male hybrids mate with purebred females. Over time, this can lead to the genetic swamping of native populations by introduced species. Native cutthroat trout populations, for instance, have been compromised by hybridization with introduced rainbow trout in many watersheds. And this brings us to the larger picture of conservation, of threats, of the precarious status of native trout species. Nearly all native trout species face conservation threats, with 92% at some level of risk. Of 28 native trout species and subspecies in North America, 3 are extinct and 6 are federally listed as threatened or endangered. Excluding extinct species, 52%, 13 of 25, occupy less than 25% of their historical habitat and face high risk from at least one major threat. Bull trout, Gila trout, and multiple steelhead populations are protected under the Endangered Species Act. The threats are numerous, but 2 stand out as most serious: climate change and non-native species, and they act in tandem, each making the other worse. Climate change is compounding traditional problems by lengthening wildfire seasons, increasing drought severity, warming cold water habitats, and facilitating the spread of warm water invasive species like smallmouth bass into former trout habitat. As water warms, bass can survive where they couldn't before, invading upstream, consuming young trout, competing for food. The April snowpack has declined across 3/4 of western states since 1955, reducing summer stream flows critical for trout survival. Less snow in the mountains means less meltwater feeding streams in summer, means lower flows, warmer water, less habitat. Bull trout distribution is particularly sensitive to air and water temperature changes caused by global warming. Bull trout need the coldest water of all trout species. As habitat warms even slightly, they disappear, retreating to smaller and smaller refuges of cold water, becoming isolated, vulnerable. It's a sobering picture. Native trout evolved over millennia to specific watersheds, specific conditions. Now face rapid environmental change they cannot adapt to quickly enough. And humans, who caused many of these problems through introduction of non-native species, habitat destruction, and climate change, now struggle to fix what we've broken. But there is hope. Conservation efforts continue. Barriers are installed to keep invasive species out of critical habitats. Restoration projects improve stream conditions. Hatchery practices improve. And people who love trout work tirelessly to protect them, to preserve what remains, to restore what was lost. The trout's future is uncertain, but it's not hopeless. Not yet. And that's where we'll rest for now. We've explored the genetic architecture of trout, the ways humans have manipulated their reproduction and chromosomes, the threats they face, the uncertain future ahead. It's heavy material, perhaps, but important. Understanding the challenges helps us appreciate what remains, motivates us to protect it. Close your eyes. Breathe. Think of a cold stream in wilderness, trout holding in clear water, persisting despite everything, ease still here, still alive. We're near the end now. Just a bit more to go. Rest if you need to. We'll finish this journey together soon. Chapter 10. We're in the home stretch now, moving through these final facts about trout with the same gentle pace we've maintained all night. If you're still here, still listening, still drifting along with us, then you've learned an extraordinary amount about these remarkable fish. And if you've been sleeping through parts of it, well, that's exactly what this was designed for. A journey you can take consciously or unconsciously, awake or asleep. In this segment, we're going to explore something fascinating: the inner life of the trout. Their ability to communicate, to learn, to remember, their aggression, and their territories. The surprising complexity of behavior in a creature we might have thought of as simple. So settle in one more time. Let your breathing be slow and steady. And let's discover just how sophisticated a trout's mind really is. Let's start with something you might not have expected. Trout make sounds. Male trout produce sounds during spawning to attract females. Male rainbow trout make low-pitched buzzing or vibrating sounds during spawning season by vibrating their bodies as they swim alongside females. It's a physical vibration, a trembling of the entire body that creates sound waves in the water. Steelhead and rainbow trout also produce feeding-related noises, including slashing, clicking, and scraping sounds, though the exact purpose remains unclear. Perhaps these sounds are incidental, byproducts of the physical act of striking prey or crushing shells, or perhaps they serve some communicative function we don't yet understand. These vocalizations are part of their mating ritual and communication repertoire, and they're quite distinctive. Rainbow trout produce these buzzing or humming sounds during spawning by vibrating their bodies as they swim alongside females. These spawning vocalizations can be heard clearly underwater during the spring spawning season and represent an important part of their mating ritual. Imagine it, a male trout swimming alongside a female on the red, his entire body vibrating with low-frequency sound. A love song performed without vocal cords, just muscle and bone resonating in water. And spawning isn't the only context for sound production. Trout produce sounds in various contexts, including territorial defense and stress responses. Fish in general produce sounds for reproductive purposes, territorial defense, and during stressful situations, including predator attacks or when handled by fishermen. Male fish typically produce sounds to attract receptive females or warn off rival males. It's communication, plain and simple. Not as complex as birdsong or whale song, perhaps, but communication nonetheless. Messages sent and received through the medium of water. Interestingly, brown trout appear to vocalize more frequently than rainbow trout based on angler observations. Perhaps they're more talkative, more communicative, more socially complex in ways we're only beginning to understand. Sound travels approximately 5 times faster underwater than in air. We mentioned this earlier, allowing trout to gather directional information from acoustic signals. They can hear another trout's buzz, determine its direction, respond appropriately. It's a sensory world we can barely imagine, where sound is not just louder, but travels with such speed and clarity that it becomes a precise navigation tool. Now let's talk about something even more surprising: learning and memory. Trout demonstrate cognitive flexibility and can learn through operant conditioning. Operant conditioning is the type of learning where behavior is modified by its consequences. Do something, get a reward. Learn to do it more often. It's how we train dogs, how we teach children, and it turns out how trout can learn too. Studies using operant conditioning devices show that rainbow trout successfully perform serial reversal learning tasks. That's a technical way of describing something quite sophisticated. The trout learn that one stimulus is rewarded and another isn't. Then the experimenters switch it. Now the previously unrewarded stimulus gives a reward, and the trout learn the new rule. Then it switches again, and again. The trout successfully switch between rewarded and unrewarded stimuli multiple times, demonstrating cognitive flexibility. They're not just learning by rote, not just forming a single fixed association. They're learning a meta rule, that the rules can change and they need to pay attention and adapt. Fish reared in enriched environments performed better in both acquisition and reversal learning phases, needing fewer trials to reach learning criteria. Enriched environments, tanks with structure, variation, stimulation, produce smarter fish. It's the same principle that applies to mammals. Environmental complexity promotes cognitive development. And here's perhaps the most impressive finding. Trout can generalize learned rules, applying a rewarded color to any shape. They learn blue means reward, and can apply that to blue circles, blue squares, blue triangles. They've abstracted the concept of color from the specific shape. That's genuine generalization, genuine conceptual thinking. For a fish, that's remarkable. It suggests an inner mental life richer than we might have assumed. Not consciousness as we experience it, perhaps, but something. Some form of awareness, flexibility, learning capacity that deserves respect. Let's talk now about personality differences between species. Rainbow trout are more active and aggressive than brown trout. Behavioral studies comparing the two species show that rainbow trout are more active and, interestingly, shier when tested individually. That seems paradoxical. More aggressive but shyer. But it makes sense in context. Rainbow trout are more aggressive than both diploid and triploid brown trout when competing for resources. But when tested individually, without social context, they're more cautious, more reactive to potential threats. However, rainbow trout become bolder than brown trout when tested in groups, suggesting their behavior is highly influenced by the presence of conspecifics, other members of their own species. It's social facilitation, the phenomenon where presence of others changes behavior. Rainbow trout gain confidence in groups, become bolder, more willing to take risks. Brown trout remain more consistent, whether alone or in groups. Different strategies, different social dynamics. Neither is better or worse. They're just different ways of navigating the world. Different behavioral profiles shaped by evolution and genetics. Now let's talk about one of the most iconic trout behaviors, jumping. Rainbow trout can jump up to 3 meters, almost 10 feet, high under the right conditions. That's an extraordinary athletic feat for a fish that might only be 1.5 feet long. 3 meters. Imagine jumping 6 times your own height. That's what trout are capable of during spawning migrations. Though, to be clear, this usually refers to low-grade waterfalls rather than vertical heights. The trout isn't leaping straight up like a salmon clearing a dam. It's using the turbulent water at the base of the waterfall, the plunge pool, to gain momentum and power, swimming and leaping in a single, fluid motion up the angled face of the falling water. Brook trout can jump over waterfalls as high as 73.5 centimeters, about 2.5 feet, provided the plunge pool below is at least 40 centimeters deep. The depth of the plunge pool matters. It gives the fish room to accelerate, to build up speed before the leap. But trout don't jump only to navigate waterfalls. Trout jump for multiple reasons beyond pursuing food. They leap from the water to loosen eggs and milt during the spawning season. A female heavy with eggs might jump to help release them, to work them down toward the vent where they'll be deposited. They jump to flush debris from their gills. If sediment or algae or particles clog the delicate gill filaments, a vigorous leap and splash might help clear them. They jump to escape predators. A heron strikes, misses by inches, and the trout launches itself away, hoping to land in deeper water, in safety. And they jump to navigate waterfalls during spawning migrations, as we've discussed. Rainbow trout, in particular, are known to leap from the water when they're hooked, in an attempt to shake the hook and escape. It's desperation, survival instinct, an explosion of energy focused on one goal: freedom. Anyone who's hooked a rainbow trout knows this behavior. The fish breaks the surface, twists in midair, shakes its head violently, crashes back down. Sometimes it works. The hook pulls free. Sometimes it doesn't. But the trout tries again and again, because not trying means certain death. Finally, let's return to something we touched on earlier, but is worth restating: social behavior. Trout do not naturally school, but may form loose aggregations based on social dynamics. While many fish species exhibit true schooling behavior, swimming in the same direction, in a coordinated manner, moving as one, trout are not obligate schoolers. They don't need to school. They're capable of solitary existence. But rainbow trout do form social hierarchies and dominant structures. Aggression and agonistic interactions are common, especially around feeding areas, where resources are concentrated, where food is predictable and abundant. Hierarchies develop. Dominant fish establish priority access. Subordinate fish learn their place, learn to wait, learn to feed when the dominant fish allow it. Wild-caught trout tend to eat more and sooner when in visual contact with another fish than in isolation, suggesting some social facilitation of feeding behavior. Seeing another fish feed triggers the impulse to feed. Perhaps it's competition. Get food before the other fish takes it all. Perhaps it's social learning. If another fish is eating, that means food is available and safe to pursue. Either way, it demonstrates that trout are aware of other trout, that they monitor each other's behavior, that they adjust their own behavior based on social context. They're not just reacting to physical environment, water flow, temperature, oxygen. They're reacting to social environment too, the presence and behavior of other fish. And that makes them more complex, more interesting, more worthy of our attention and respect than we might have initially thought. And that's where we'll rest for now. We've discovered that trout can communicate through sound, that they can learn and remember and generalize, that different species have different personalities, that they jump for many reasons, and that their behavior is shaped by social context in sophisticated ways. Trout are not simple creatures. They're not mindless automatons responding mechanically to stimuli. They're learning, adapting, communicating creatures with individual differences, species differences, behavioral flexibility. They deserve our respect, and they deserve our protection. Rest now. We're nearly at the end. Just one more section to go. Breathe slowly. Let everything we've learned settle like sediment in still water. We'll finish this journey together soon. Chapter 11. And here we are at the final stretch of our journey through the night. We've traveled so far together, learned so much about these remarkable fish. From their bones and muscles, to their senses and behaviors, from their spawning rituals, to their genetic code. And now, in these last moments before sleep fully claims you, or before morning arrives, whichever comes first, we're going to explore the connection between trout and humans. How we use them, value them, eat them, and share this world with them. So take a deep breath, let it out slowly, and let's bring this journey home. Let's start with a practical question. Are trout good to eat? And if so, what makes them nutritionally valuable? Rainbow trout contains substantial omega-3 fatty acids. Those beneficial fats we're always told to consume more of, though significantly less than salmon. A 100-gram serving of farmed rainbow trout provides approximately 0.73 grams of combined DHA and EPA omega-3 fatty acids. For comparison, farmed Atlantic salmon offers 1.96 grams, almost 3 times as much. But here's the thing. A cooked serving of farm-raised rainbow trout still contains approximately 981 milligrams of omega-3 fatty acids. That far exceeds the World Health Organization's minimum daily requirement of 300 to 500 milligrams. So while trout has less than salmon, it still provides more than enough for your daily needs. Wild rainbow trout contains approximately 0.44 grams EPA and 0.40 grams DHA per 100 gram portion. Wild fish tend to have slightly different nutritional profiles than farmed fish, depending on what they eat, how much they swim, the temperature of the water they live in. Trout is also relatively lean. It has a relatively low fat content of 2 to 5%, with approximately 6.3 grams of fat per serving, while also providing high-quality protein. Rainbow trout is classified as a medium-fat fish. For comparison, salmon is a high-fat fish, while cod or tilapia are low-fat fish. Trout sits comfortably in the middle. A 3-ounce serving of cooked rainbow trout provides 143 calories, 0 carbohydrates, 0 fiber, 20 grams of protein, and only 52 milligrams of sodium. It's a clean, simple food. Protein and healthy fats, minimal sodium, no carbohydrates. Trout also provides vitamin D for bone growth and minerals essential for human health. It's no wonder trout has been a valued food source for thousands of years. From indigenous peoples fishing mountain streams to modern consumers buying fillets at the grocery store. And that brings us to aquaculture, to the raising of trout in hatcheries for food and for stocking into recreational waters. Trout hatcheries play a major role in recreational fishing through fish stocking programs. Modern hatcheries stock hundreds of thousands of trout annually for recreational purposes. Raising brook, rainbow, brown, and even tiger trout, a hybrid, from fingerlings to catchable size. The general stocking recommendation is 200 to 400 fish per surface acre of pond, with different species suited to different temperature ranges. Rainbow trout tolerate warmer water than brook trout. Brown trout are even more temperature tolerant. Matching the species to the conditions improves survival and growth. Some hatcheries have converted to recirculating aquaculture systems, RAS as they're called, that can produce nearly triple the amount of fish, using only 25% of the original water flow. These systems filter and reuse water, maintaining water quality through biological and mechanical filtration, dramatically reducing water consumption and environmental impact. It's efficient, intensive aquaculture, producing large numbers of fish in relatively small spaces with minimal water use. Some people find it troubling. Fish raised in tanks in artificial conditions. Others see it as the future of sustainable protein production, far less environmentally damaging than land-based livestock. Either way, it's a major industry. The trout industry represents a significant economic sector worth billions globally. The global trout market reached 1,005,300 metric tons in 2024 and is projected to grow to 1,163,000 metric tons by 2033. In the United States alone, the rainbow trout industry is valued at $1.45 billion in 2025 and expected to reach $2.10 billion by 2035. U.S. trout aquaculture sales totaled $134.1 million in 2023, with Idaho leading production at $41.45 million. The total value of food-size fish sold reached $109.6 million. These aren't small numbers. Trout farming is big business, providing jobs, feeding people, supporting rural economies in states like Idaho, North Carolina, Pennsylvania, and others. Now let's talk about the giants, the record holders, the trout that grew to extraordinary size. The world record brown trout weighed 44 pounds, 5 ounces. Sumas Petri caught this current IGFA world record brown trout in New Zealand's Ohau Canal in October 2020. It measured 38.58 inches long with a 34-inch girth. Imagine a brown trout, nearly 40 inches long, as thick around as a person's thigh. It's an ancient fish, a survivor, a creature that found ideal conditions and grew to massive size. The world record lake trout is even more massive at 72 pounds, caught by Lloyd Bull in Canada's Great Bear Lake in 1995. Lake trout can live for decades in the cold, deep lakes they inhabit, growing slowly but steadily to enormous size. A 72-pound fish might be 40 or 50 years old, a creature that was swimming when your parents were young, that survived through decades of changing conditions. How do scientists determine how old a trout is? Trout age is determined by counting annular rings on otoliths, scales, or fin rays. It's like counting tree rings, but on fish bones. Scientists typically count annuli, annual growth rings, from the core to the edge of calcified structures to estimate age. Otoliths, those ear bones we mentioned way back at the beginning, provide the most accurate age determinations. They're bones that continue growing throughout the fish's life, adding layers each year. Pelvic fin rays are next in accuracy, while scales are less precise, especially for fish older than age 4. Scales can be reabsorbed during periods of stress or spawning, confusing the count. Annulus formation in fin rays occurs between late April and early June, validated through mark recapture studies where scientists tag fish, release them, and catch them again years later to verify aging techniques. Let's go microscopic now, into the blood and gut of the trout, where complex biochemistry and microbial ecosystems exist. Trout blood contains multiple distinct hemoglobin components with different properties. At least 3 major hemoglobin components exist in trout blood, and all erythrocytes, red blood cells, contain all components. It's not that some cells have one type and others have another. Each cell contains all 3 types. Different hemoglobin types have varying oxygen-binding properties and responses to pH changes. Some bind oxygen tightly, some more loosely. Some are more affected by acidification, others less so. This gives trout blood flexibility, adaptability to different conditions. Some components show significant differences in amino acid sequences, up to 39.6% difference between major trout hemoglobin types. That's a huge variation. They're essentially different proteins doing similar jobs, but with different performance characteristics. Hemoglobin makes up 56 to 65% of total heme protein by weight in trout. The rest is myoglobin in mussels and other heme-containing enzymes. But the majority is hemoglobin, that oxygen-carrying molecule that makes blood red. And in the gut, an entire ecosystem exists. Trout gut microbiota is dominated by 5 bacterial phyla, with distinct differences between farmed and wild fish. The core microbiota of brook and rainbow trout consists primarily of proteobacteria, actinobacteria, firmicutes, fusobacteriota, and bacteroidata. Together, these represent approximately 90% of gut microorganisms. Farmed trout show a significantly higher presence of fusobacteria, 37 to 44%, particularly the genus Cetobacterium, which is not detected in wild trout samples. Wild brook trout have substantially higher percentages of bacilli, up to 68%. What does this mean? It means diet and environment shape the gut microbiome. Farmed trout eating processed feed develop different bacterial communities than wild trout eating insects and small fish. And those bacterial communities affect digestion, nutrition, immune function, even behavior. Diet composition and gut location dramatically alter the trout microbiome. Plant-based protein diets significantly increase the abundance of Mycoplasma bacteria, 52 to 76% of gut microbiota, compared to fish meal diets in rainbow trout, particularly under handling stress. In wild brook trout, firmicutes dominate intestinal contents, 57%, while proteobacteria dominate the intestinal wall, 52%. Different bacteria colonize the food passing through versus the gut lining itself, indicating different functional roles across gut compartments. Some bacteria specialize in breaking down food. Others interact with the gut wall, possibly influencing immune function or nutrient absorption. It's a hidden world, invisible to the naked eye, but crucial to the trout's health and function. Let's pull back now to the big picture, to evolutionary time and ecological impact. The evolutionary history of trout spans millions of years. Brown trout lineages diverged within the last 0.5 to 2 million years during the Pleistocene glaciation cycles. The Atlantic lineage originated approximately 0.611 million years ago, separating from Mediterranean populations as ice sheets advanced and retreated. The first known ancestral cutthroat trout, the truckee trout, dates back 10 million years. 10 million years. Dinosaurs had been extinct for 55 million years by then, but humans wouldn't appear for another 9.5 million years. Trout were here long before us. Despite this long history, invasive trout species now pose serious threats to native populations. Brown trout, native to Europe and Western Asia, have been introduced worldwide and are now ranked among the top 30 worst invasive species globally. They outcompete native trout, hybridize with them, alter ecosystems. Native bull trout and cutthroat trout occupancy in Montana is declining significantly as waters warm due to climate change. As water warms, native cold water specialists disappear, replaced by more temperature-tolerant species. Sometimes non-native trout, sometimes warm water fish, like bass and catfish. It's a reminder that even trout, beloved by anglers, beautiful and charismatic, can be invasive pests when introduced to places they don't belong. Conservation is complex. Sometimes the trout we want to protect are threatened by other trout we've introduced. But where trout belong, where they evolved, they play a crucial role. Trout are keystone species in aquatic ecosystems. We've mentioned this before, but it bears repeating as we close. As mid-level predators, trout play a crucial role in maintaining ecosystem balance. They prey on smaller aquatic animals, insects, small fish, crustaceans, keeping those populations in check. They serve as important food for larger predators, bears, eagles, otters, herons, and their remains provide nutrients for scavengers and riparian plants. When a trout dies and washes onto the bank, its body returns nutrients from the aquatic ecosystem to the terrestrial ecosystem: nitrogen, phosphorus, carbon, elements that came from the stream, processed through the trout's body, now feeding plants and soil organisms on land. It's a connection, a link between water and land, between prey and predator, between life and death and new life. Trout are part of a web, a network of relationships that extends far beyond the fish themselves. And that's where our journey ends. We've traveled through 110 facts about trout, from their bones to their blood, from their spawning to their survival, from their genetics to their gut bacteria, from their ancient origins to their uncertain future. We've learned that trout are complex, sophisticated, beautifully adapted creatures, that they face serious threats from climate change, pollution, invasive species, and habitat destruction, that they provide food and recreation for millions of people, that they play crucial ecological roles, that they deserve our respect and our protection. If you're still awake, congratulations. You've made it through more than 2 hours of facts about trout. If you've been sleeping, that's wonderful too. You got exactly what you came for: a gentle voice speaking quietly about cold water fish, while you drifted off to dreams. Either way, thank you for taking this journey with us. Thank you for spending this night learning about, or sleeping to, the secret life of trout. May your dreams be peaceful. May you sleep deeply, and may you wake refreshed, perhaps with a new appreciation for those remarkable fish that hold steady in cold streams, that have been here for millions of years, that persist despite everything beautiful and resilient and endlessly fascinating. Good night, friend. Sleep well. The trout will still be there in the morning, holding in the current, waiting.